Welcome to our exploration of the intriguing world of physics, where we delve into the complexities and limitations of special relativity. In this video, we'll uncover why special relativity, despite its profound impact, fails to fully explain the universe. Special relativity, introduced by Albert Einstein in 1905, revolutionized our understanding of space and time. It showed that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is constant, regardless of the observer's motion. These groundbreaking insights reshaped physics and paved the way for modern technology. However, as revolutionary as it is, special relativity has its limitations. One of the most significant is its inability to incorporate gravity. While it explains the behavior of objects moving at constant speeds, it does not account for the force that governs the motion of planets, stars, and galaxies. This gap led Einstein to develop general relativity, which extends special relativity to include gravity. General relativity describes how massive objects warp the fabric of space-time, creating the gravitational effects we observe. Yet, even general relativity doesn't solve all the puzzles of the universe. Another major challenge for special relativity is its incompatibility with quantum mechanics. Quantum mechanics governs the behavior of particles at the smallest scales, where the rules of classical physics break down. Reconciling these two foundational theories remains one of the biggest unsolved problems in physics. Moreover, special relativity fails to explain dark matter, an elusive substance that makes up about 27% of the universe. Despite extensive research, scientists have yet to directly detect dark matter, and its nature remains one of the biggest mysteries in astrophysics. Similarly, dark energy, which accounts for roughly 68% of the universe, is another phenomenon that special relativity cannot explain. Dark energy is thought to be responsible for the accelerated expansion of the universe, but its true nature is still unknown. In the realm of high-energy physics, special relativity falls short in explaining phenomena observed in particle accelerators. These experiments have revealed discrepancies that challenge our understanding and suggest the need for new theories beyond special relativity. Efforts to unify physics through theories like string theory and loop quantum gravity highlight the limitations of special relativity. These advanced theories aim to reconcile general relativity and quantum mechanics, offering a more comprehensive framework for understanding the universe. As we venture further into the unknown, it becomes clear that while special relativity is a cornerstone of modern physics, it is not the final word. Its limitations push us to seek deeper, more encompassing theories that can address the mysteries of the cosmos. One significant shortcoming of special relativity is its inability to explain gravity. While special relativity transformed our understanding of space and time, it left out the crucial aspect of how gravity works in the universe. Gravity is the force that governs the motion of celestial bodies, from planets orbiting stars to galaxies forming clusters. Special relativity, however, only deals with objects moving at constant speeds in the absence of gravitational forces. This limitation became evident when trying to apply special relativity to scenarios involving massive objects. The theory simply couldn't account for the gravitational attraction between them, leading to incomplete descriptions of their interactions. Einstein recognized this gap and worked on developing a more comprehensive theory. The result was general relativity, published in 1915, which extended his earlier work to include gravitational effects. In general relativity, gravity is not seen as a force, but as a curvature of space-time caused by mass and energy. Massive objects like planets and stars warp the fabric of space-time around them, and this curvature directs the motion of other objects. This new perspective revolutionized our understanding of gravity, providing explanations for phenomena that special relativity couldn't address. For example, the bending of light around massive objects, known as gravitational lensing, is accurately described by general relativity. Another crucial phenomenon explained by general relativity is the orbit of Mercury. Its perihelion shift, or the point of closest approach to the Sun, could not be fully explained by Newtonian mechanics, but match predictions made by general relativity. Black holes, regions of space where gravity is so intense that not even light can escape, are another prediction of general relativity. These enigmatic objects provide critical insights, into the extreme effects of gravity that special relativity could not predict. Moreover, general relativity has been confirmed by numerous experiments and observations. From the precise measurements of time dilation near massive objects to the detection of gravitational waves, the evidence supporting general relativity is overwhelming. Despite its successes, general relativity also has its limitations, particularly in the quantum realm. However, it remains the best theory we have for describing gravitational phenomena, illustrating the shortcomings of special relativity in this area. Special relativity's framework simply doesn't accommodate the concept of curved spacetime. It treats space and time as a flat, unchanging backdrop, which is inadequate for explaining gravitational interactions. The development of general relativity was a monumental leap forward, filling in the gaps left by special relativity. It showed that our universe is far more complex and interconnected than previously thought, with gravity playing a pivotal role. Special relativity's inability to explain gravity underscores the need for theories that encompass a broader range of physical phenomena. While it laid the groundwork for modern physics, it also highlighted the necessity of continuous exploration and refinement of our understanding. Understanding the limitations of special relativity is essential for grasping the full picture of how our universe operates. It serves as a reminder that scientific theories are constantly evolving, driven by the quest to explain the mysteries of nature. As we continue to push the boundaries of knowledge, the interplay between special relativity and general relativity remains a fascinating and crucial area of study, paving the way for future breakthroughs. Another significant issue with special relativity is its incompatibility with quantum mechanics. These two pillars of modern physics describe vastly different realms and struggle to coexist within a unified framework. Quantum mechanics governs the behavior of particles at the smallest scales, where the peculiarities of the subatomic world dominate. It introduces concepts like wave-particle duality, superposition, and entanglement, which defy classical intuition. Special relativity, on the other hand, excels in describing the motion of objects moving at high speeds, particularly when approaching the speed of light. However, it doesn't account for the probabilistic nature of particles at the quantum level. One major area of conflict is the concept of locality. Special relativity insists that information cannot travel faster than the speed of light, maintaining a strict cause and effect relationship. Quantum mechanics, however, features phenomena like entanglement, where particles seem to influence each other instantaneously, regardless of distance. This apparent violation of locality in quantum mechanics challenges the very foundation of special relativity. Experiments such as those involving Bell's theorem have shown that entangled particles can exhibit correlations that defy classical explanations, suggesting the need for a deeper understanding. Another point of contention is the uncertainty principle, a core tenet of quantum mechanics. It states that certain pairs of properties like position and momentum cannot be simultaneously known to arbitrary precision. Special relativity, however, operates within a framework where such uncertainties are not inherently accounted for. In the quest to unify these theories, physicists have developed quantum field theory, which attempts to reconcile quantum mechanics with special relativity. This framework describes particles as excitations in underlying fields, allowing for a more integrated approach. Despite the success of quantum field theory in many areas, it still encounters difficulties, particularly when dealing with gravity. Incorporating gravitational effects into a quantum framework remains a significant challenge, as seen in the attempts to develop a quantum theory of gravity. String theory is one such attempt to bridge this gap. It proposes that the fundamental constituents of the universe are not point particles, but tiny, vibrating strings. These strings operate within a higher dimensional space, potentially reconciling quantum mechanics with both special and general relativity. Another approach is loop quantum gravity, which seeks to quantize space-time itself. This theory envisions space-time as a network of discrete loops, aiming to integrate quantum principles with the curvature of space-time described by general relativity. However, these theories remain largely theoretical, with limited experimental verification. They illustrate the profound difficulty in creating a comprehensive framework that accommodates both the relativistic and quantum realms. The incompatibility between special relativity and quantum mechanics highlights the need for new paradigms in physics. As researchers delve deeper into the fabric of the universe, they continue to uncover complexities that challenge existing theories. Understanding the nuances and limitations of both special relativity and quantum mechanics is crucial for advancing our knowledge. It drives the development of new models that strive to provide a more unified and complete description of nature. This ongoing effort underscores the dynamic and evolving nature of scientific inquiry. Each discovery and theoretical development brings us closer to a deeper understanding, yet also reveals new questions and challenges. The interplay between these two foundational theories remains a central focus in physics. It exemplifies the intricate and interconnected nature of the universe, where answers often lead to new and profound mysteries. Special relativity also falls short in its inability to explain dark matter, a mysterious and invisible substance that makes up about 27% of the universe. Despite its significance, dark matter remains one of the most elusive components in cosmology. Evidence for dark matter first emerged from observations of galactic rotation curves. Astronomers noticed that the outer regions of galaxies were rotating much faster than could be explained by the visible mass alone, indicating the presence of unseen matter. This unseen matter, termed dark matter, doesn't interact with electromagnetic forces, making it invisible and detectable only through its gravitational effects. Special relativity, with its focus on high-speed motion and lack of gravitational considerations, offers no insights into this phenomenon. Various observations support the existence of dark matter, including the behavior of galaxy clusters and gravitational lensing, where light from distant objects is bent by unseen mass. These observations point to a substantial amount of non-luminous matter affecting the universe. Special relativity's framework doesn't include mechanisms to account for these gravitational anomalies. Its equations and principles are designed for situations devoid of such invisible influences, highlighting a significant gap in its explanatory power. One approach to understanding dark matter involves the search for weakly interacting massive particles, or WIMPs. These hypothetical particles are thought to make up dark matter, interacting only through gravity and the weak nuclear force. However, their detection remains elusive. Experiments around the world are dedicated to finding direct evidence of dark matter particles. These include underground detectors designed to sense rare interactions between dark matter and ordinary matter, but so far results have been inconclusive. Alternative theories, such as modified Newtonian dynamics or MOND, attempt to explain galactic rotation curves without invoking dark matter. MOND suggests modifications to Newton's laws at low accelerations, but it too lacks integration with special relativity. Despite these efforts, the true nature of dark matter remains one of the greatest unsolved mysteries in physics. Its existence challenges our understanding of the universe and calls for theories that extend beyond the scope of special relativity. Special relativity's inability to address dark matter highlights its limitations in describing the full complexity of cosmic phenomena. This gap underscores the need for new theories that can encompass both visible and invisible components of the universe. In cosmology, the distribution of dark matter is mapped through its gravitational influence on visible matter. These maps reveal large-scale structures like filaments and voids, shaping our understanding of the universe's architecture. While special relativity revolutionized our comprehension of space and time, it didn't anticipate the complexities introduced by dark matter. The ongoing quest to understand this invisible substance drives much of modern astrophysics and cosmology. The search for dark matter involves a multidisciplinary approach, combining observations, theoretical models, and cutting-edge experiments. It illustrates the dynamic and interconnected nature of scientific research, where each discovery opens new avenues for exploration. Understanding dark matter is crucial for a complete picture of the universe. It affects the formation and evolution of galaxies, influences cosmic microwave background radiation, and plays a role in the overall dynamics of the cosmos. As we continue to probe the mysteries of dark matter, we acknowledge the limitations of our current theories. Special relativity, while foundational, is part of a broader tapestry of scientific knowledge that must evolve to explain the unseen and unknown aspects of our universe. Another significant limitation of special relativity is its failure to address dark energy, a mysterious force driving the accelerated expansion of the universe. Dark energy is even more enigmatic than dark matter, constituting about 68% of the universe's total energy density. The concept of dark energy emerged from observations of distant supernovae in the late 1990s. These observations revealed that the universe's expansion is accelerating, contrary to the expectation that gravity should be slowing it down. This surprising discovery pointed to the existence of an unknown form of energy permeating space. Special relativity, with its focus on the relationship between space and time for objects in inertial frames, doesn't offer any mechanisms to explain this acceleration. It lacks the framework to account for a repulsive force that influences the universe on a cosmic scale. Dark energy is often associated with the cosmological constant, a term Einstein originally introduced in his field equations of general relativity. He later discarded it, calling it his greatest blunder, but it was revived to explain the accelerated expansion. This cosmological constant represents a constant energy density filling space homogeneously. While general relativity accommodates the cosmological constant, special relativity remains silent on the matter. The theory's scope doesn't extend to the dynamics of the universe's large-scale structure or its expansion history. The nature of dark energy is still one of the biggest questions in cosmology. It could be a property of space itself, or it might be explained by new undiscovered particles or fields. Current theories suggest possibilities like quintessence, a dynamic field that changes over time, unlike the static cosmological constant. Observations from the cosmic microwave background radiation, the large-scale structure of the universe, and galaxy clusters all provide indirect evidence for dark energy. These data sets collectively reinforce the notion of an accelerating universe, driven by an unknown energy component. However, special relativity, which excels in describing high-speed particles and electromagnetic fields, offers no insights into this cosmic acceleration. The theory's equations don't include terms that would account for a universal repulsive force. To better understand dark energy, scientists turn to general relativity and its modifications. Various models propose different mechanisms, but all seek to extend beyond what special relativity can describe. The lambda CDM model, which includes both dark matter and dark energy as a cosmological constant, is currently the most accepted model. Special relativity's framework was not designed to tackle the complexities of an evolving, accelerating cosmos. Its principles, while revolutionary for their time, are insufficient for addressing phenomena that operate on scales far beyond the realm of high-speed travel and local interactions. The pursuit of understanding dark energy involves numerous observations and experiments, including those conducted by space telescopes and ground-based observatories. These efforts aim to measure the universe's expansion rate with increasing precision and to unravel the properties of dark energy. As with dark matter, the inability of special relativity to explain dark energy highlights the need for more comprehensive theories. These new theories must integrate the principles of relativity with those of quantum mechanics and cosmology to provide a fuller picture of the universe. The study of dark energy is a testament to the evolving nature of physics. Each new discovery challenges existing paradigms and pushes the boundaries of what we know. Special relativity's limitations in this area underscore the importance of continual scientific advancement and adaptation. Understanding dark energy is not just about solving a single problem. It's about piecing together the fundamental aspects of our universe's past, present, and future. It requires a collaborative effort across various fields of physics and astronomy, driving innovation and discovery. As we delve deeper into the mysteries of dark energy, we acknowledge the foundational role of special relativity while also recognizing its boundaries. This journey illustrates the ever-evolving quest for knowledge that defines the scientific endeavor. Special relativity also faces limitations when it comes to high-energy physics. At extremely high energies, the interactions and behaviors of particles reveal complexities that special relativity cannot fully address. Particle accelerators, like the Large Hadron Collider, smash particles together at nearly the speed of light. These collisions produce conditions similar to those just after the Big Bang, allowing scientists to study fundamental forces in particles. However, special relativity, which accurately describes the behavior of objects at constant high speeds, struggles to explain certain phenomena observed in these high-energy environments. The theory doesn't incorporate the quantum effects that dominate at these scales. High-energy physics experiments have revealed the existence of numerous subatomic particles and interactions. The standard model of particle physics, which describes these particles and their interactions, incorporates special relativity but extends beyond it to include quantum mechanics. One significant area where special relativity falls short is in describing the strong nuclear force, which binds protons and neutrons in atomic nuclei. Quantum chromodynamics, the theory describing this force, requires a quantum framework that special relativity alone cannot provide. Additionally, special relativity does not account for the electroweak force, a unification of the electromagnetic and weak nuclear forces. The electroweak theory, part of the standard model, successfully integrates quantum mechanics with relativity to explain particle interactions at high energies. The discovery of the Higgs boson at the Large Hadron Collider further illustrates the limitations of special relativity. The Higgs mechanism, which gives particles mass, is a quantum field theory phenomenon that doesn't fit within the framework of special relativity alone. Furthermore, phenomena such as neutrino oscillations, where neutrinos change flavors as they travel, challenge the completeness of special relativity. These oscillations suggest that neutrinos have mass, requiring extensions to the standard model that incorporate both quantum mechanics and relativity. Supersymmetry, a proposed extension of the standard model, aims to resolve some of these high-energy discrepancies. It predicts the existence of superpartner particles, providing a more unified framework. However, it remains a theoretical construct, not yet confirmed by experiments. Special relativity also encounters difficulties with the concept of renormalization in quantum field theories. Renormalization deals with infinities that arise in calculations, a process essential for making meaningful predictions in high-energy physics. The pursuit of a grand unified theory, which seeks to unify the fundamental forces of nature, highlights the gaps in special relativity. These efforts point to the necessity of a theory that encompasses both high-energy interactions and gravitational effects. The extreme conditions in the early universe, moments after the Big Bang, further illustrate the limitations of special relativity. Understanding these conditions requires a theory that integrates quantum mechanics with gravity, a challenge that special relativity does not address. Black hole physics is another realm where high-energy phenomena expose the shortcomings of special relativity. Near a black hole's event horizon, gravitational and quantum effects interplay in ways that demand a more comprehensive theoretical framework. The quest for a quantum theory of gravity, which includes efforts like string theory and loop quantum gravity, seeks to bridge these gaps. These theories aim to provide a unified description of all fundamental forces, transcending the limitations of special relativity. In high-energy physics, the limitations of special relativity become evident, driving the need for more advanced theories. As we explore the most fundamental aspects of the universe, we continue to build on the foundation laid by special relativity, seeking a deeper understanding of the cosmos. While special relativity revolutionized our understanding of space and time, it couldn't explain gravity. This gap led Einstein to develop a more comprehensive theory, general relativity. Published in 1915, general relativity extends special relativity to include gravitational effects. General relativity is based on the idea that gravity is not a force between masses, but a curvature of space-time caused by mass and energy. Massive objects warp the fabric of space-time, creating what we perceive as gravity. This was a profound shift from the Newtonian view of gravity as a force acting at a distance. One of the key concepts in general relativity is the equivalence principle. It states that the effects of gravity are indistinguishable from the effects of acceleration. This principle laid the groundwork for understanding gravity as a geometric property of space-time. Einstein's field equations are the core of general relativity. These equations describe how matter and energy influence the curvature of space-time. Solving these complex equations provides insights into various gravitational phenomena. A significant prediction of general relativity is the bending of light by gravity, known as gravitational lensing. Light passing near a massive object like a star or galaxy is bent, causing the object to appear displaced from its true position. This effect has been confirmed by numerous observations. Another critical prediction is the existence of black holes. These are regions of space where gravity is so intense that nothing, not even light, can escape. The concept of black holes has been supported by observational evidence, such as the detection of X-rays from accretion disks and the behavior of stars orbiting invisible massive objects. General relativity also explains the precession of Mercury's orbit. The point of Mercury's closest approach to the Sun shifts over time, a phenomenon that couldn't be fully explained by Newtonian mechanics. General relativity accurately predicts this precession. The theory has been confirmed by many experiments and observations. One of the most famous tests was the 1919 solar eclipse expedition led by Sir Arthur Eddington. The observed bending of starlight around the Sun during the eclipse matched Einstein's predictions, providing strong evidence for general relativity. Another fascinating aspect of general relativity is time dilation near massive objects. Clocks run slower in stronger gravitational fields. This effect has been measured in experiments with atomic clocks on Earth and in space, confirming the theory's predictions. General relativity also predicts gravitational waves, ripples in the fabric of space-time, caused by accelerating massive objects. The first direct detection of gravitational waves was made by the LIGO Observatory in 2015, a century after Einstein's prediction. This discovery opened a new window into observing the universe. Despite its successes, general relativity is not without challenges. It breaks down at the quantum scale, where the effects of quantum mechanics become significant. This incompatibility drives the ongoing search for a theory of quantum gravity. General relativity has profound implications for cosmology. It provides the framework for understanding the large-scale structure of the universe, the dynamics of galaxies, and the behavior of cosmic phenomena. It also forms the basis for models of the universe's expansion and the Big Bang theory. The theory has also influenced our understanding of time and causality. The warping of space-time leads to phenomena such as time dilation and the possibility of wormholes, theoretical passages through space-time that could connect distant regions of the universe. General relativity's impact extends beyond physics, influencing fields like astronomy, cosmology, and even philosophy. It challenges our notions of space, time, and reality, pushing the boundaries of human knowledge. As we continue to explore the universe, general relativity remains a cornerstone of our understanding. Its predictions and insights guide our investigations into the cosmos, highlighting the intricate and dynamic nature of space and time. Einstein's field equations are the cornerstone of general relativity. They describe how matter and energy in the universe influence the curvature of space-time. These equations are a set of 10 interrelated differential equations, complex and challenging to solve. The field equations can be summarized by a simple but profound statement. Mass and energy tell space-time how to curve, and curved space-time tells objects how to move. This relationship forms the foundation of our understanding of gravity and general relativity. One of the key components of Einstein's field equations is the Einstein tensor. This tensor encapsulates the curvature of spacetime. It is constructed from the metric tensor, which defines the geometry of spacetime, and the Ricci curvature tensor, which describes how much spacetime is curved by matter and energy. On the other side of the equation is the stress-energy tensor. This tensor represents the distribution and flow of energy and momentum throughout spacetime. It includes contributions from matter, radiation, and other forms of energy. Einstein's field equations equate the Einstein tensor to the stress-energy tensor, scaled by a constant factor known as the gravitational constant. This relationship captures the essence of how matter and energy influence the geometry of the universe. Solving these equations for specific scenarios provides insights into various gravitational phenomena. For instance, the Schwarzschild solution describes the space-time geometry around a spherical, non-rotating mass like a star or planet. This solution predicts the existence of black holes. Another important solution is the Kerr metric, which extends the Schwarzschild solution to rotating masses. This solution describes the space-time around rotating black holes, revealing phenomena such as frame dragging, where space-time itself is twisted by the rotating mass. The Friedmann-Lemaitre-Robertson-Walker (FLRW) metric is a solution to Einstein's equations that describes a homogeneous, isotropic expanding or contracting universe. This solution forms the basis for modern cosmological models, including the Big Bang theory. Einstein's field equations also predict the existence of gravitational waves. These are ripples in the fabric of space-time generated by accelerating masses, such as merging black holes or neutron stars. The detection of gravitational waves has confirmed this prediction, providing new ways to observe and study the universe. The complexity of Einstein's field equations means that exact solutions are rare and often involve simplifying assumptions. Numerical relativity, which uses computational methods to solve these equations, has become an essential tool for studying systems where exact solutions are not feasible, such as binary black hole mergers. The field equations also reveal the concept of space-time singularities, regions where the curvature of space-time becomes infinite. Black holes are examples of such singularities. Understanding these extreme conditions remains a significant challenge in theoretical physics. In cosmology, the field equations underpin models of the universe's evolution. They describe how the universe has expanded from the Big Bang, how it continues to evolve, and how it might end. These models help scientists understand the large-scale structure and dynamics of the cosmos. Einstein's field equations have profound implications for our understanding of gravity. They shift the perspective from a force acting at a distance, as in Newtonian gravity, to a geometric property of space-time itself. This paradigm shift has transformed our approach to physics and cosmology. Despite their successes, the field equations also highlight the need for a theory of quantum gravity. At quantum scales, the smooth fabric of space-time, predicted by general relativity, breaks down. Reconciling these equations with quantum mechanics remains a central goal in theoretical physics. The ongoing study of Einstein's field equations continues to push the boundaries of our knowledge. They are not just mathematical expressions, but are keys to understanding the very nature of reality, guiding us in exploring the fundamental aspects of the universe. The concept of the curvature of space-time is central to general relativity. This idea fundamentally changes how we perceive gravity, not as a force, but as the warping of space and time by mass and energy. Massive objects like stars and planets create curves in the fabric of space-time. Smaller objects move along these curves, which we perceive as gravitational attraction. This curvature is described mathematically by the metric tensor in Einstein's field equations. An analogy often used to explain space-time curvature is a heavy ball placed on a stretched rubber sheet. The ball creates a dent, and smaller balls placed on the sheet will roll towards the heavier ball, simulating gravitational pull. This analogy helps visualize how mass warps space-time. The amount of curvature depends on the mass and energy of an object. More massive objects create deeper and more extensive curves. This effect can be observed in gravitational lensing, where light from distant stars bends around massive objects like galaxies, creating multiple images or distorted shapes. Another manifestation of space-time curvature is the phenomenon of time dilation. Clocks closer to a massive object, within a stronger gravitational field, tick slower compared to those further away. This effect has been confirmed by experiments with atomic clocks on Earth and in orbit. Black holes represent extreme curvature of space-time. Their gravitational pull is so intense that it creates a point of infinite curvature, known as a singularity, surrounded by an event horizon beyond which nothing can escape. The study of black holes provides critical insights into the nature of space-time under extreme conditions. The curvature of space-time also affects the orbits of planets and the paths of light rays. For example, Mercury's orbit around the Sun precesses in a way that couldn't be explained by Newtonian physics, but fits perfectly within the framework of general relativity. Space-time curvature is not static. It can change and propagate. This dynamic aspect is seen in gravitational waves, ripples in space-time generated by massive accelerating objects, like merging black holes. These waves travel at the speed of light, carrying information about their origins. The curvature of space-time can be visualized using embedding diagrams, which represent a two-dimensional slice of space-time curved into a third dimension. These diagrams help illustrate how gravity affects the geometry of space around massive objects. In cosmology, the curvature of space-time is used to describe the overall shape and evolution of the universe. Depending on the density of matter and energy, the universe can be open, closed, or flat. These shapes influence the universe's fate, whether it will expand forever, collapse back on itself, or reach a steady state. Einstein's theory of general relativity, with its concept of curved spacetime, has passed numerous tests and observations, from the bending of starlight during eclipses to the precise tracking of planetary orbits. These validations strengthen our understanding of gravity as a geometric property. Spacetime curvature also plays a role in the study of cosmic inflation, a rapid expansion of the universe after the Big Bang. This expansion smoothed out initial irregularities, leading to the large-scale structure we observe today. The study of inflation involves understanding how spacetime itself can stretch and evolve. The interplay between spacetime curvature and quantum mechanics is a frontier of modern physics. Theories like quantum field theory in curved spacetime attempt to describe how particles behave in a curved spacetime background, providing insights into phenomena like Hawking radiation from black holes. Understanding spacetime curvature is crucial for the development of technologies like GPS, which must account for relativistic time dilation to provide accurate positioning. This application demonstrates how theoretical concepts in physics have practical implications in everyday life. The exploration of spacetime curvature continues to push the boundaries of our knowledge, challenging our perceptions of reality and guiding us towards a deeper understanding of the universe's fundamental structure. As we delve further into this concept, we uncover new questions and pathways in the quest to comprehend the cosmos. Black holes are among the most intriguing predictions of general relativity. They are regions in space where gravity is so intense that nothing, not even light, can escape. This extreme gravitational pull warps space-time to create a singularity at the center. A singularity is a point where density becomes infinite, and the laws of physics as we know them break down. Around this singularity lies the event horizon, the boundary beyond which no information or matter can return. This makes black holes fascinating yet challenging objects to study. The formation of black holes typically occurs when massive stars exhaust their nuclear fuel. Without the outward pressure from nuclear fusion, gravity causes the star to collapse under its own weight, forming a black hole. This process leads to a concentration of mass and a dramatic curvature of space-time. Black holes come in different sizes, from stellar mass black holes formed by collapsing stars to supermassive black holes found at the centers of galaxies. These supermassive black holes have millions to billions of times the mass of our Sun and play crucial roles in galaxy formation and evolution. One of the most striking features of black holes is their ability to distort light. This effect, known as gravitational lensing, occurs when light from a background object passes near a black hole and bends around it. This creates multiple images, rings, or arcs, providing a unique way to study these objects. The discovery of black holes has been confirmed through various observational techniques. One method is by observing the motion of stars and gas near the black hole. These objects move at incredibly high speeds due to the black hole's gravity, revealing its presence even if the black hole itself cannot be seen. Accretion disks are another telltale sign of black holes. As matter falls into a black hole, it forms a spinning disk of hot, glowing gas. The intense gravitational forces heat this material to extreme temperatures, causing it to emit X-rays. These X-ray emissions can be detected by telescopes, providing evidence of a black hole. Black holes are also sources of powerful jets. In some cases, the magnetic fields around a black hole can accelerate particles to nearly the speed of light, creating jets that extend for thousands of light years. These jets can influence the environment of the host galaxy, affecting star formation and the interstellar medium. Hawking radiation is a theoretical prediction that black holes can emit radiation due to quantum effects near the event horizon. This radiation causes black holes to lose mass over time, eventually leading to their evaporation. This concept combines principles from quantum mechanics and general relativity, offering insights into the nature of black holes and the fabric of space-time. The study of black holes has advanced significantly with the detection of gravitational waves. These ripples in space-time are produced by the merger of black holes. The first direct detection of such waves in 2015 by the LIGO Observatory confirmed another of Einstein's predictions and opened a new era in astrophysics. Black holes challenge our understanding of physics, especially in the realm of singularities. At a singularity, the curvature of space-time becomes infinite, and the known laws of physics cease to function. This points to the need for a theory of quantum gravity that can describe these extreme conditions. Research into black holes also explores the possibility of information paradoxes. According to quantum mechanics, information about physical states cannot be destroyed, but it seems to disappear in a black hole. Resolving this paradox is a key question in theoretical physics. Wormholes, hypothetical tunnels through space-time, are solutions to Einstein's field equations that could theoretically connect distant parts of the universe. While no evidence for wormholes exists, they remain a popular subject of speculation and research in the context of black holes and general relativity. Black holes also provide a testing ground for the limits of general relativity. By studying these objects, scientists can test the predictions of the theory under extreme conditions, seeking any deviations that might hint at new physics. The exploration of black holes and singularities continues to push the boundaries of our knowledge, offering profound insights into the nature of gravity, space-time, and the universe itself. Each discovery brings us closer to understanding these enigmatic objects and their place in the cosmic landscape. Experimental evidence for general relativity has been accumulating since its inception. One of the earliest confirmations came from the 1919 solar eclipse expedition led by Sir Arthur Eddington. During the eclipse, Eddington observed the bending of starlight by the sun's gravity, matching Einstein's predictions and providing a dramatic validation of the theory. The perihelion shift of Mercury's orbit is another key piece of evidence. Mercury's orbit precesses around the Sun, a phenomenon that couldn't be fully explained by Newtonian mechanics. General relativity accurately accounts for this shift, demonstrating its superiority in describing gravitational effects. Gravitational redshift is another confirmation of general relativity. This effect occurs when light or other electromagnetic radiation from a source in a strong gravitational field is shifted to longer wavelengths. Experiments such as the Pound-Rebka experiment in 1959 confirmed this prediction with high precision. The Global Positioning System, or GPS, provides everyday evidence of general relativity. GPS satellites orbit Earth and must account for time dilation effects predicted by general relativity to provide accurate positioning. Without these relativistic corrections, GPS would be inaccurate by several kilometers. Observations of binary pulsars have provided further support for general relativity. These systems, consisting of two neutron stars orbiting each other, emit gravitational waves as predicted by Einstein's theory. The energy lost due to these waves causes the stars to spiral towards each other, a behavior precisely matching general relativity's predictions. The detection of gravitational waves is one of the most spectacular confirmations of general relativity. First observed by LIGO in 2015, these waves are ripples in space-time caused by the acceleration of massive objects like merging black holes. This discovery has opened a new window into observing and understanding the universe. Frame dragging, another prediction of general relativity, has been confirmed by experiments such as Gravity Probe B. This effect occurs when massive rotating objects like Earth twist the space-time around them. The probe measured this subtle effect, providing further evidence for Einstein's theory. Gravitational lensing is a phenomenon where light from distant objects is bent by the gravity of massive objects like galaxies or galaxy clusters. This effect not only confirms general relativity, but also provides a powerful tool for studying dark matter and the large-scale structure of the universe. The cosmic microwave background radiation, the afterglow of the Big Bang, shows patterns that are consistent with general relativity's predictions about the early universe. These patterns have been observed by satellites like COBE, WMAP, and Planck, further cementing the theory's accuracy. Black hole observations also support general relativity. The Event Horizon Telescope's image of the supermassive black hole in the galaxy M87 provides visual evidence of the shadow and event horizon predicted by the theory. These observations match theoretical models based on general relativity. Time dilation in strong gravitational fields has been observed in various contexts. For instance, atomic clocks flown on airplanes or placed at different altitudes show that time runs slower in stronger gravitational fields, confirming Einstein's predictions about time dilation. Tests of the equivalence principle, a cornerstone of general relativity, have been conducted with increasing precision. Experiments like the microscope satellite mission confirm that objects in free fall experience the same acceleration regardless of their mass or composition, upholding the equivalence principle to a high degree of accuracy. Lunar laser ranging experiments, which involve bouncing laser beams off reflectors placed on the Moon, have provided precise measurements of the Earth-Moon distance. These experiments confirm general relativity's predictions about the Moon's orbit and the effects of Earth's gravity on space-time. The study of neutron stars and their extreme gravitational fields offers another testing ground for general relativity. Observations of these dense objects, including their rotational speeds and the gravitational waves they emit, continue to match the predictions made by Einstein's theory. General relativity has withstood a century of scrutiny and experimental testing. Each piece of evidence not only confirms the theory's predictions, but also deepens our understanding of the universe's fundamental workings. The ongoing quest to test and validate general relativity exemplifies the dynamic and ever-evolving nature of scientific inquiry. Wave-particle duality is a fundamental concept in quantum mechanics, describing how particles like electrons and photons exhibit both wave-like and particle-like properties. This duality challenges our classical understanding of physics and introduces a new way of thinking about the nature of matter and energy. The duality was first observed in light. In the early 20th century, experiments showed that light behaves as a wave, capable of interference and diffraction. However, the photoelectric effect, explained by Einstein, revealed that light also behaves as a particle, with discrete packets of energy called photons. Electrons, traditionally considered particles, also display wave-like behavior. The famous double-slit experiment demonstrated this. When electrons pass through two slits and are detected on a screen, they create an interference pattern typical of waves, even when sent one at a time. This experiment underscores the bizarre nature of quantum mechanics. Electrons appear to interfere with themselves, suggesting they travel as waves, but are detected as particles. This duality implies that particles do not have definite paths but exist in a state of probability until measured. Wave-particle duality is described mathematically by the Schrödinger equation, which provides a wave function representing the probability distribution of a particle's position and momentum. This wave function evolves over time, guiding the behavior of particles in a probabilistic manner. The concept extends to all matter, not just light and electrons. De Broglie hypothesized that particles such as protons and even larger objects have wave-like properties, with wavelengths inversely proportional to their momentum. This was later confirmed through experiments with particles like neutrons and atoms. Quantum mechanics requires a new interpretation of measurement. The act of measuring a particle collapses its wave function, causing it to behave like a particle. Before measurement, it exists in a superposition of states, simultaneously occupying multiple possibilities. This wave-particle duality leads to the uncertainty principle, articulated by Heisenberg. It states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This inherent uncertainty is a direct consequence of wave-like behavior. The duality is crucial for understanding phenomena like electron diffraction and the behavior of particles in a quantum well. It also explains the stability of atoms, where electrons occupy discrete energy levels due to their wave-like nature, preventing them from spiraling into the nucleus. In quantum field theory, particles are seen as excitations of underlying fields, further blending the concepts of particles and waves. This framework unifies wave-particle duality with the principles of relativity, providing a more comprehensive understanding of fundamental interactions. Wave-particle duality also influences technologies like electron microscopy and quantum computing. Electron microscopes use the wave properties of electrons to achieve high-resolution imaging, while quantum computers exploit superposition and entanglement to perform complex calculations. The duality has philosophical implications, challenging our perceptions of reality. It suggests that particles do not have intrinsic properties independent of observation, highlighting the role of the observer in defining physical phenomena. Debates about the interpretation of quantum mechanics, such as the Copenhagen interpretation versus the many-worlds theory, revolve around wave-particle duality. These discussions explore the nature of reality, determinism, and the limits of human knowledge. Experiments continue to probe the boundaries of wave-particle duality, testing the principles of quantum mechanics in increasingly complex systems. These studies aim to deepen our understanding of the quantum world and its connection to classical physics. Wave-particle duality remains a cornerstone of quantum mechanics, illustrating the intricate and often counterintuitive nature of the quantum realm. It continues to inspire research, technological innovation, and philosophical inquiry, shaping our quest to comprehend the fundamental nature of the universe. Quantum entanglement is one of the most perplexing and fascinating phenomena in quantum mechanics. It describes a situation where particles become so deeply linked that the state of one instantly influences the state of another, no matter the distance separating them. This phenomenon was first identified by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 in a paper known as the EPR paradox. They used entanglement to argue that quantum mechanics was incomplete, as it implied spooky action at a distance, which Einstein famously disliked. Despite Einstein's skepticism, entanglement has been confirmed by numerous experiments. When two particles are entangled, their properties, such as spin, polarization, or position, become correlated. Measuring one immediately determines the state of the other, even if they are light years apart. This instantaneous connection appears to violate the principle that information cannot travel faster than the speed of light. However, entanglement does not transmit usable information in this way, so it does not contradict relativity. Instead, it highlights the non-local nature of quantum mechanics. Bell's theorem, formulated by physicist John Bell in 1964, provided a way to test the reality of quantum entanglement. Bell's inequalities showed that no local hidden variable theory could reproduce all the predictions of quantum mechanics. Experiments have consistently violated these inequalities, supporting the existence of entanglement. One of the most famous experiments confirming entanglement was conducted by Alain Aspect in the 1980s. His work demonstrated that entangled particles remain connected regardless of the distance, providing strong evidence against local hidden variables and solidifying entanglement as a fundamental aspect of nature. Entanglement has profound implications for our understanding of reality. It suggests that particles are not independent entities but part of a connected whole. This interconnectedness challenges classical notions of separability and individuality in physical systems. Quantum entanglement plays a crucial role in various quantum technologies. In quantum computing, entangled qubits allow for the performance of complex calculations much faster than classical computers. Quantum cryptography uses entanglement to create secure communication channels, making eavesdropping impossible without detection. Quantum teleportation is another application of entanglement. This process involves transferring the state of a particle to another particle at a distant location, effectively teleporting the information. This has been experimentally demonstrated over distances of up to hundreds of kilometers. Entanglement also aids in precision measurements and sensing. Quantum metrology uses entangled states to achieve higher sensitivity and accuracy than classical methods, improving technologies like atomic clocks and gravitational wave detectors. The study of entanglement extends to macroscopic systems, exploring whether large objects can exhibit quantum entanglement. Researchers are investigating the boundaries between quantum and classical worlds, potentially leading to new insights into the nature of quantum coherence and decoherence. Entanglement entropy is a measure of the degree of entanglement in a quantum system. This concept has applications in quantum information theory and condensed matter physics, helping to understand phenomena such as phase transitions and quantum critical points. Entanglement also plays a role in understanding black holes and the information paradox. The idea that information about matter falling into a black hole is preserved in entangled pairs suggests possible resolutions to this long-standing problem in theoretical physics. Experiments continue to push the boundaries of our knowledge of entanglement, investigating its properties and potential applications. These studies aim to harness entanglement for practical technologies while deepening our understanding of quantum mechanics. Quantum entanglement remains one of the most intriguing aspects of modern physics. It challenges our understanding of space, time, and information, opening new frontiers in both theoretical and applied physics. As research advances, entanglement promises to revolutionize technology and expand our comprehension of the quantum world. The uncertainty principle is a fundamental concept in quantum mechanics, introduced by Werner Heisenberg in 1927. It states that certain pairs of physical properties, like position and momentum, cannot both be precisely known at the same time. This inherent limitation is not due to measurement errors, but to the nature of quantum systems. According to the uncertainty principle, the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This relationship is mathematically expressed by Heisenberg's uncertainty equation, which places a lower bound on the product of the uncertainties. This principle challenges classical physics, where it was assumed that with perfect instruments, we could measure any property to arbitrary precision. In the quantum realm, this is not possible, as the very act of measuring one property disturbs the other. The uncertainty principle arises from the wave-particle duality of matter. Particles like electrons exhibit both wave-like and particle-like properties. The wave function describing a particle spreads out in space, meaning it doesn't have a single definite position, which in turn affects the precision with which we can know its momentum. This principle has profound implications for our understanding of reality. It implies that at a fundamental level, nature is probabilistic rather than deterministic. The outcomes of measurements are not predetermined, but are governed by probabilities. One classic demonstration of the uncertainty principle is the diffraction of electrons through a narrow slit. As the slit width decreases to better define the electron's position, the spread of possible momenta increases, leading to a broader diffraction pattern on the other side. Another implication is the zero-point energy of systems. Even at absolute zero temperature, quantum systems possess inherent fluctuations due to the uncertainty principle. These fluctuations prevent particles from being completely at rest, influencing phenomena such as the stability of atoms and the behavior of superconductors. The uncertainty principle also affects the energy levels of atoms. Electrons in atoms occupy discrete energy levels because their positions and momenta are constrained by the uncertainty principle. This quantization of energy levels underpins the structure of atoms and the emission spectra of elements. In quantum field theory, the uncertainty principle explains the existence of virtual particles. These particles pop in and out of existence, mediating forces and interactions between particles. These transient fluctuations are a direct consequence of the uncertainty in energy and time. Quantum tunneling is another phenomenon explained by the uncertainty principle. Particles can pass through potential barriers that would be insurmountable in classical physics. This effect is crucial in many processes, including nuclear fusion in stars and the operation of modern electronic devices like transistors. The uncertainty principle also sets limits on the precision of measurements in quantum experiments. Technologies such as the laser interferometers used in gravitational wave detectors are designed to operate at the limits imposed by quantum uncertainty, pushing the boundaries of precision measurement. Heisenberg's uncertainty principle is not just a theoretical construct, but has practical implications in various fields of science and technology. It guides the design of experiments and the development of new technologies, ensuring that our measurements are as accurate as the laws of physics allow. In quantum computing, the uncertainty principle plays a role in the behavior of qubits, the fundamental units of quantum information. The superposition and entanglement of qubits are influenced by the constraints imposed by the uncertainty principle, affecting how quantum information is processed and stored. Philosophically, the uncertainty principle challenges our understanding of reality and causality. It suggests that the universe at its most fundamental level is governed by probabilities and uncertainties, reshaping our notions of determinism and predictability. Research continues to explore the depths of the uncertainty principle, investigating its implications and applications. This ongoing inquiry not only deepens our understanding of quantum mechanics, but also drives advancements in technology and experimental techniques. The uncertainty principle remains a cornerstone of quantum mechanics, embodying the strange and counterintuitive nature of the quantum world. It shapes our comprehension of physical reality, guiding both theoretical exploration and practical innovation in the quest to unlock the secrets of the universe. Quantum field theory, or QFT, is the framework that combines quantum mechanics with special relativity. It describes how particles and fields interact at the quantum level, providing a comprehensive description of the fundamental forces of nature. In QFT, particles are seen as excitations or quanta of underlying fields. Each type of particle corresponds to a specific field, like the electromagnetic field for photons or the electron field for electrons. These fields permeate all of space and interact with each other according to the rules of quantum mechanics. The development of QFT began in the early 20th century, with key contributions from physicists like Paul Dirac, Richard Feynman, and Julian Schwinger. It was developed to address the shortcomings of earlier quantum theories, particularly in describing the interactions between particles at high energies. One of the central concepts in QFT is the creation and annihilation operators, which describe how particles are produced and destroyed in interactions. These operators act on the quantum fields to create particle states, allowing the theory to account for processes like particle collisions and decays. Feynman diagrams are a powerful tool in QFT, providing a visual representation of particle interactions. These diagrams depict the exchange of virtual particles between interacting particles, simplifying the calculation of probabilities for various quantum processes. QFT successfully describes three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. The theory underlying electromagnetism is quantum electrodynamics, or QED, which describes how charged particles interact with the electromagnetic field. Quantum chromodynamics, or QCD, is the QFT that describes the strong nuclear force, which binds quarks together to form protons and neutrons. QCD explains how quarks interact through the exchange of gluons, the carriers of the strong force, resulting in the complex structure of hadrons. The electroweak theory unifies the electromagnetic and weak nuclear forces into a single theoretical framework. This unification was accomplished by Sheldon Glashow, Abdus Salam, and Steven Weinberg, who showed that these forces are different manifestations of a single underlying interaction. The Higgs field, introduced in the standard model of particle physics, explains how particles acquire mass. The interaction with the Higgs field gives particles their mass, with the Higgs boson being the quantum of this field. The discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed this crucial aspect of QFT. QFT also predicts the existence of antiparticles for every particle, a concept first proposed by Dirac. Antiparticles have the same mass as their corresponding particles, but opposite charges. When a particle meets its antiparticle, they annihilate each other, releasing energy. Renormalization is a key technique in QFT, addressing the problem of infinities that arise in calculations of particle interactions. This process redefines the parameters of the theory to produce finite, physically meaningful results, allowing precise predictions that match experimental data. Despite its successes, QFT faces challenges, particularly in incorporating gravity. General relativity, the current theory of gravity, is not easily reconciled with the principles of QFT, leading to ongoing efforts to develop a quantum theory of gravity, such as string theory or loop quantum gravity. Supersymmetry is an extension of QFT that posits a symmetry between fermions and bosons, potentially solving some of the theoretical problems in the standard model and providing a pathway to unifying all fundamental forces. However, experimental evidence for supersymmetry remains elusive. QFT has profound implications for our understanding of the universe, from the behavior of fundamental particles to the dynamics of the early universe. It provides the theoretical foundation for much of modern physics, influencing fields such as condensed matter physics, cosmology, and particle physics. The ongoing development of QFT continues to push the boundaries of our knowledge, seeking to answer fundamental questions about the nature of reality. As experiments probe deeper into the quantum realm, QFT remains an essential tool for interpreting the results and guiding future discoveries. Evidence for dark matter comes from a variety of astronomical observations. One of the earliest indicators was the rotation curves of galaxies. In the 1970s, astronomer Vera Rubin observed that stars in the outer regions of galaxies were rotating at speeds that couldn't be explained by the visible matter alone, suggesting the presence of unseen mass. Another compelling piece of evidence is the cosmic microwave background radiation. This faint glow left over from the Big Bang shows slight temperature fluctuations that correspond to density variations in the early universe. These variations imply a significant amount of non-luminous matter affecting the growth of cosmic structures. Gravitational lensing provides further evidence. When light from distant galaxies passes near a massive object like a galaxy cluster, it bends and magnifies, creating multiple images or distorted arcs. The amount of bending indicates more mass than can be accounted for by visible matter alone, pointing to the presence of dark matter. Galaxy clusters themselves offer clues. The total mass of a cluster, inferred from the motion of galaxies within it, gravitational lensing, and X-ray emissions from hot gas, is much greater than the mass of the visible galaxies and gas. This discrepancy suggests a large amount of unseen dark matter. Observations of the large-scale structure of the universe support the existence of dark matter. The distribution and movement of galaxies across vast cosmic distances follow patterns that require dark matter to explain their formation and alignment. The Bullet cluster provides a particularly striking piece of evidence. This cluster resulted from the collision of two smaller galaxy clusters. Observations show that the visible matter, mainly hot gas, was slowed by the collision, but the gravitational lensing maps indicate most of the mass, associated with dark matter, passed through without slowing, revealing the separation of dark and visible matter. Studies of the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe, show that dark matter provides the gravitational scaffolding necessary for the formation of galaxies and clusters. Simulations that include dark matter closely match the observed distribution of galaxies. In the realm of particle physics, experiments aim to detect dark matter particles directly. These include deep underground detectors, designed to observe rare interactions between dark matter and normal matter. Although direct detection has yet to succeed, these experiments help refine our understanding of dark matter properties. Indirect detection methods look for signals produced when dark matter particles annihilate or decay. These searches involve observing gamma rays, neutrinos, or other particles that might result from dark matter interactions, using telescopes and detectors on Earth and in space.
The rotation of dwarf galaxies also provides insights. These small galaxies exhibit rotation speeds that suggest they are dominated by dark matter, providing another piece of the puzzle in understanding the distribution of dark matter in different types of galaxies.
Weak gravitational lensing, which measures the subtle distortions of light from distant galaxies by intervening dark matter, maps the distribution of dark matter on large scales. These maps align well with theoretical predictions, further confirming the existence and distribution of dark matter. The behavior of galaxy mergers offers additional evidence. During these events, the stars and gas in galaxies interact differently from the dark matter. Observations of such mergers reveal that dark matter behaves as if it is collisionless, maintaining its distribution even when visible matter is disrupted. Dark matter is essential for explaining the observed rate of galaxy formation and evolution. Models of galaxy formation that include dark matter accurately reproduce the sizes, shapes, and distributions of galaxies seen today, supporting the idea that dark matter plays a critical role in cosmic history. The success of the lambda CDM model, which includes dark matter and dark energy, in describing the universe's expansion and structure formation, provides indirect evidence. This model matches observations from the cosmic microwave background, galaxy clustering, and supernova distances, reinforcing the necessity of dark matter in cosmology. Ongoing research continues to refine our understanding of dark matter, combining observations across multiple scales and techniques. Each piece of evidence strengthens the case for dark matter, highlighting its vital role in shaping the universe as we observe it today. Galactic rotation curves have provided some of the most compelling evidence for the existence of dark matter. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford made a groundbreaking discovery while studying the rotation curves of spiral galaxies. A rotation curve plots the orbital velocity of stars or gas in a galaxy against their distance from the galaxy's center. According to Newtonian mechanics, we would expect the rotation speeds to decrease with distance from the center, similar to the planets in our solar system. However, Rubin and Ford observed that in many spiral galaxies, the rotation speeds of stars remained constant or even increased with distance from the center. This flat rotation curve was unexpected and couldn't be explained by the visible mass of the galaxies alone. If only the visible matter were present, the outer regions of galaxies would rotate much more slowly than observed. The constant high speeds imply that there must be additional unseen mass providing the necessary gravitational pull to keep the stars moving quickly. This unseen mass is what we call dark matter. The presence of dark matter in the outer regions of galaxies explains the flat rotation curves. It suggests that galaxies are surrounded by massive invisible halos of dark matter. The dark matter halo extends far beyond the visible edge of the galaxy, containing much more mass than the visible components. These halos are thought to dominate the total mass of galaxies, influencing their rotation and overall structure. The consistency of flat rotation curves across many different galaxies strengthens the case for dark matter. Whether in small dwarf galaxies or large spiral galaxies, the same pattern emerges, indicating a universal property of galaxy dynamics. Observations of gas clouds in galaxies also support the dark matter hypothesis. These clouds, like stars, exhibit high orbital speeds at large distances from the galactic center, reinforcing the idea of an extended mass distribution. Alternative theories, such as modified Newtonian dynamics, MOND, have been proposed to explain the flat rotation curves without invoking dark matter. MOND suggests modifications to Newton's laws at low accelerations, but it faces challenges in explaining all observational data consistently. Detailed studies of individual galaxies, including the Milky Way, reveal similar rotation curve behavior. These studies map the distribution of stars, gas, and dark matter, providing a comprehensive picture of galactic mass distribution. Computer simulations of galaxy formation and evolution, which include dark matter, successfully reproduce the observed rotation curves. These simulations show how dark matter influences the formation and dynamics of galaxies, from the early universe to the present day. The impact of dark matter on galactic rotation is also observed in elliptical galaxies, although their rotation curves are less straightforward than those of spirals. In these galaxies, dark matter still plays a crucial role in their mass distribution and dynamics. Gravitational lensing studies further support the presence of dark matter in galaxies. The lensing effects depend on the total mass, including dark matter, and align with the mass distributions inferred from rotation curves. The study of galactic rotation curves continues to be a vital area of research in astrophysics. It provides crucial insights into the nature and distribution of dark matter, shaping our understanding of galaxy formation and the structure of the universe. As observational techniques improve, we continue to refine our models of galactic rotation and dark matter. Each new discovery adds to our knowledge, helping to unravel the mysteries of dark matter and its profound influence on the cosmos. Weakly interacting massive particles, or WIMPs, are one of the leading candidates for dark matter. These hypothetical particles are thought to have mass and interact through the weak nuclear force, but not through electromagnetic or strong nuclear forces, making them invisible and difficult to detect. WIMPs are an attractive dark matter candidate because their properties naturally arise from theories beyond the standard model of particle physics. They would have been produced in the right abundance in the early universe to account for the observed amount of dark matter. One of the key characteristics of WIMPs is their weak interaction with normal matter. This weak interaction means they rarely collide with atoms, allowing them to pass through ordinary matter without being detected, yet exerting gravitational effects. The search for WIMPs involves several approaches. Direct detection experiments aim to observe the rare collisions between WIMPs and atomic nuclei. These experiments are typically conducted deep underground to shield them from cosmic rays and other background radiation. One such experiment is the Large Underground Xenon (LUX) detector. It uses a tank of liquid xenon to detect flashes of light and ionization caused by a WIMP collision with a xenon nucleus. Although LUX has not yet detected WIMPs, it has set stringent limits on their properties. Another prominent direct detection experiment is the Cryogenic Dark Matter Search, CDMS. This experiment uses supercooled germanium and silicon detectors to identify the heat and ionization produced by WIMP interactions. Like LUX, CDMS continues to refine the search parameters for WIMPs. Indirect detection searches look for the products of WIMP annihilations or decays. If WIMPs annihilate each other, they could produce gamma rays, neutrinos, or other particles. Observatories like the Fermi Gamma Ray Space Telescope scan the sky for excess gamma rays that might signal WIMP activity. In addition to gamma rays, neutrino detectors like IceCube in Antarctica look for high-energy neutrinos from potential WIMP annihilations in the Sun or the center of the galaxy. These neutrinos would provide indirect evidence of WIMPs if detected in significant quantities. Collider experiments, such as those conducted at the Large Hadron Collider, LHC, also search for WIMPs. By smashing protons together at high energies, physicists hope to produce WIMPs directly, or observe missing energy signatures indicating WIMP production. WIMPs are predicted by several theoretical models, including supersymmetry. Supersymmetry proposes that each particle in the standard model has a superpartner, with the lightest supersymmetric particle potentially being a WIMP. This theory provides a natural dark matter candidate. Despite extensive searches, WIMPs have yet to be detected. This has led scientists to consider alternative dark matter candidates, such as axions or sterile neutrinos, and to explore different interaction models and parameter spaces for WIMPs. The ongoing search for WIMPs involves international collaborations and a variety of experimental techniques. Each new experiment and observation helps to narrow down the properties that WIMPs might have, guiding future research efforts. Understanding WIMPs is crucial for solving the dark matter puzzle. If discovered, WIMPs would not only explain dark matter, but also provide insights into new physics beyond the standard model, potentially leading to a deeper understanding of the universe. The quest to detect WIMPs continues to drive innovation in experimental physics. New technologies and methodologies are constantly being developed to improve the sensitivity and accuracy of dark matter searches. As we probe deeper into the nature of dark matter, WIMPs remain a leading candidate. The search for these elusive particles embodies the challenges and excitement of exploring the unknown, pushing the boundaries of our scientific knowledge. The discovery of WIMPs would be a monumental breakthrough in physics, transforming our understanding of the cosmos and revealing the nature of the dark matter that shapes the structure and evolution of the universe. While dark matter remains the leading explanation for various cosmic phenomena, alternative theories have been proposed to address the same observations. One prominent alternative is modified Newtonian dynamics, or MOND. MOND suggests that Newton's laws of motion need to be altered at very low accelerations to account for the observed behavior of galaxies. MOND was introduced by physicist Mordechai Milgram in the early 1980s. According to MOND, the force of gravity does not follow the inverse square law at extremely low accelerations, which are common in the outer regions of galaxies. Instead, the gravitational force becomes stronger than predicted by Newtonian mechanics, which could explain the flat rotation curves of galaxies without invoking dark matter. The success of MOND in explaining galactic rotation curves has garnered attention, but it also faces significant challenges. One major issue is its difficulty in explaining observations at larger cosmic scales, such as galaxy clusters and the cosmic microwave background, where dark matter models perform well. Another alternative to dark matter is modified gravity, often represented by theories like TVS, tensor vector scalar gravity. TVS is a relativistic generalization of MOND, developed to be compatible with general relativity. It introduces additional fields to explain the dynamics of galaxies and galaxy clusters while addressing some of the limitations of MOND. Emergent gravity, proposed by Eric Verlinde, is another intriguing theory. Verlinde suggests that gravity is not a fundamental force, but an emergent phenomenon arising from the microscopic degrees of freedom of space-time. This theory aims to derive the laws of gravity from first principles and could potentially explain the effects attributed to dark matter. Self-interacting. Dark matter, SIDM, is a variation within the dark matter paradigm that assumes dark matter particles interact with each other through forces other than gravity. These interactions could solve some issues that standard cold dark matter models face, such as the core cusp problem in the centers of galaxies. Fuzzy dark matter is another alternative that posits dark matter is made up of ultralight particles that form a quantum wave-like structure on galactic scales. This theory could naturally explain some of the observed properties of dark matter distributions in galaxies. Warm dark matter, WDM, is an intermediate model between cold and hot dark matter. It consists of particles that have velocities lower than hot dark matter, but higher than cold dark matter. WDM could address some small-scale structure issues that cold dark matter models encounter. Massive compact halo objects, MACOs, were once considered as a possible dark matter candidate. These include objects like black holes, neutron stars, and brown dwarfs. However, surveys and gravitational lensing studies have shown that MACOs cannot account for the majority of dark matter. Dark fluid is a theory that unifies dark matter and dark energy into a single framework. It proposes that dark matter and dark energy are different manifestations of a single underlying fluid, with properties that change over cosmic time. Entropic gravity is another speculative idea suggesting that gravity arises from the thermodynamic principles of entropy and information. In this framework, the effects attributed to dark matter might emerge from entropic considerations. Gravitational ether theories attempt to modify general relativity to account for dark matter-like effects without introducing new particles. These theories add new terms to the equations of gravity, modifying how gravity behaves on large scales. Another approach involves theories with extra dimensions, like those in string theory or brane world scenarios. These theories propose that additional spatial dimensions could influence gravitational interactions, potentially explaining dark matter effects. Variable speed of light (VSL). Theories suggest that the speed of light may have varied over cosmic time. These theories could offer alternative explanations for cosmological observations typically attributed to dark matter and dark energy. Baryon acoustic oscillations (BAO) measurements provide another test for these alternative theories. By comparing predictions from MOND, TVES, and other models with observed BAO data, scientists can assess the viability of these alternatives. While alternative theories offer fascinating insights and potential solutions to dark matter-related phenomena, none have yet matched the explanatory power and consistency of the dark matter hypothesis across all scales and observations. Ongoing research continues to explore these alternatives, seeking a deeper understanding of the universe's true nature. Experimental searches for dark matter are at the forefront of modern physics, involving a wide range of sophisticated technologies and methodologies. One major approach is direct detection, which aims to observe dark matter particles interacting with normal matter here on Earth. Direct detection experiments are typically conducted deep underground to shield them from cosmic rays and other background noise. These experiments use various materials and techniques to detect the rare interactions between dark matter particles and atomic nuclei. The LUX Zeppelin experiment is one such effort, using a large tank of liquid xenon to detect flashes of light and ionization produced when a dark matter particle collides with a xenon nucleus. This experiment seeks to achieve unprecedented sensitivity in detecting these elusive interactions. Another prominent direct detection experiment is Xenon-T, located in Italy's Gran Sasso National Laboratory. It also uses liquid xenon and has set some of the most stringent limits on dark matter properties to date, though it has yet to make a definitive detection. The Super-Cryogenic Dark Matter Search, or Super-CDMS, uses cryogenically cooled germanium and silicon detectors. These detectors are designed to detect the tiny amounts of heat and ionization that result from dark matter particles colliding with the detector material. Indirect detection searches look for signals produced when dark matter particles annihilate or decay. These searches involve detecting high-energy particles such as gamma rays, neutrinos, or positrons that could result from dark matter interactions. The Fermi Gamma Ray Space Telescope scans the sky for excess gamma rays that might indicate dark matter annihilations in regions with high dark matter density, such as the center of our galaxy. Any detected excess could provide clues about dark matter properties. Neutrino observatories like IceCube, located at the South Pole, look for high-energy neutrinos from potential dark matter annihilations in the Sun or the Milky Way's center. These neutrinos, if detected in significant quantities, could offer indirect evidence of dark matter. Collider experiments, such as those conducted at the Large Hadron Collider, LHC, search for dark matter by creating high-energy collisions between protons. These collisions could produce dark matter particles, which would escape detection but leave behind missing energy and momentum signatures. The Alpha Magnetic Spectrometer on the International Space Station searches for antimatter in cosmic rays, which could be a signal of dark matter annihilation. By measuring the types and amounts of particles in cosmic rays, this experiment aims to identify anomalies that might indicate dark matter. The Dark Energy Survey and other astronomical surveys look for gravitational effects of dark matter on large-scale structures. These surveys map the distribution of galaxies and dark matter across the universe, using weak gravitational lensing to infer the presence of dark matter. The Axion Dark Matter Experiment, or ADMX, searches for axions, another dark matter candidate, by using a strong magnetic field to convert axions into detectable microwave photons. This experiment targets a specific range of axion masses and coupling strengths. The Edelweiss experiment in France uses cryogenic germanium detectors to search for WIMPs, focusing on low-energy recoils that could be indicative of dark matter interactions. This experiment operates at extremely low temperatures to minimize thermal noise. PICO, located in Canada, uses superheated liquid detectors to search for dark matter. When a dark matter particle interacts with the liquid, it causes a tiny bubble to form, which can be detected acoustically. This method provides a different approach to detecting dark matter. The search for dark matter also extends to experiments looking for primordial black holes, which could constitute dark matter. These experiments look for microlensing events, where a primordial black hole passing in front of a star causes a temporary increase in the star's brightness. As experimental searches for dark matter continue, they employ increasingly sophisticated technology and methodologies. Each experiment, whether through direct detection, indirect detection, or collider searches, brings us closer to understanding the nature of dark matter and its role in the universe. The discovery that the universe's expansion is accelerating was one of the most surprising findings in modern cosmology. This revelation came from observations of distant Type Ia supernovae in the late 1990s by two independent teams of astronomers. Type Ia supernovae are exploding stars with consistent brightness, making them excellent standard candles for measuring cosmic distances. By comparing the apparent brightness of these supernovae with their redshifts, astronomers can determine how the universe's expansion rate has changed over time. The teams found that distant supernovae were dimmer than expected, indicating they were farther away than previously thought. This implied that the expansion of the universe was not slowing down due to gravity, as once believed, but was actually accelerating. This accelerating expansion suggests the presence of a mysterious force or energy permeating the universe, now known as dark energy. Dark energy is thought to make up about 68% of the total energy density of the universe, influencing its expansion on a cosmic scale. The nature of dark energy remains one of the biggest mysteries in cosmology. One possibility is that it is related to the cosmological constant, a term Einstein originally introduced in his field equations of general relativity to allow for a static universe. He later discarded it, but it has been revived to explain the accelerating expansion. Another possibility is that dark energy is a dynamic field, similar to the Higgs field, which evolves over time. This idea is known as quintessence. Unlike the cosmological constant, quintessence could vary in strength and distribution throughout the universe. Observations of the cosmic microwave background radiation also support the existence of dark energy. The patterns of temperature fluctuations in this afterglow of the Big Bang provide insights into the overall geometry and composition of the universe, consistent with a significant component of dark energy. Large-scale structure surveys, which map the distribution of galaxies and galaxy clusters, further reinforce the presence of dark energy. These surveys show how dark energy influences the formation and growth of cosmic structures over billions of years. Baryon acoustic oscillations, which are regular periodic fluctuations in the density of the visible baryonic matter of the universe, serve as another probe of dark energy. These oscillations leave an imprint on the distribution of galaxies, providing a standard ruler for measuring cosmic expansion. The integrated Sachs-Wolfe effect, which measures the change in energy of cosmic microwave background photons as they pass through gravitational potential wells, also provides evidence for dark energy. This effect is enhanced in a universe with dark energy, leading to observable imprints on the cosmic microwave background. Future missions and experiments aim to shed more light on the nature of dark energy. The Euclid mission by the European Space Agency and the Nancy Grace Roman Space Telescope by NASA are designed to map the geometry of the dark universe with unprecedented precision. Ground-based observatories like the Dark Energy Survey and the Large Synoptic Survey Telescope will also play a crucial role in studying dark energy. These surveys will gather vast amounts of data on galaxies, supernovae, and cosmic structures to better understand how dark energy drives the universe's expansion. Theoretical physicists are exploring various models of dark energy, from modifications to general relativity to new scalar fields and extra dimensions. These models aim to explain the properties and behavior of dark energy within a broader framework of fundamental physics. Understanding dark energy is not just a matter of cosmic curiosity. It has profound implications for the ultimate fate of the universe. Depending on the properties of dark energy, the universe could continue to expand forever, slow down, or even collapse in a big crunch. The accelerating expansion of the universe challenges our understanding of fundamental physics and the cosmos. It drives ongoing research and exploration, pushing the boundaries of what we know about the universe's past, present, and future. As we continue to study this phenomenon, we may uncover new insights into the nature of reality itself. The cosmological constant, denoted by the Greek letter lambda, L, was first introduced by Albert Einstein in 1917. He added it to his equations of general relativity to allow for a static universe, which was the prevailing view at the time. Einstein's cosmological constant acts as a repulsive force, counteracting gravity and preventing the universe from collapsing. However, when Edwin Hubble discovered in 1929 that the universe is expanding, Einstein abandoned the cosmological constant, calling it his greatest blunder. Despite Einstein's initial dismissal, the concept of the cosmological constant gained renewed interest with the discovery of the accelerating expansion of the universe in the late 1990s. This acceleration suggests that some form of energy, resembling the cosmological constant, is driving the expansion. The cosmological constant is now understood as a type of dark energy, a mysterious force that makes up about 68% of the universe's energy density. Unlike other forms of energy, it has a constant density throughout space and time, exerting a uniform repulsive pressure. In the framework of general relativity, the cosmological constant modifies the equations governing the universe's dynamics. It introduces a term that adds a constant energy density to the vacuum of space, leading to accelerated expansion. Observations of the cosmic microwave background radiation provide evidence for the cosmological constant. The patterns of temperature fluctuations in this primordial radiation are consistent with a universe that includes a significant component of dark energy. Large-scale surveys of galaxies also support the existence of the cosmological constant. These surveys map the distribution and movement of galaxies over cosmic time, showing how the universe's expansion rate has changed, consistent with a repulsive force like dark energy. The cosmological constant can be thought of as the energy of the vacuum itself. Quantum field theory predicts that empty space should have an intrinsic energy due to virtual particles constantly popping in and out of existence. However, the theoretical value of this vacuum energy is much larger than what is observed, leading to the cosmological constant problem. This discrepancy between theoretical predictions and observational data is one of the biggest unsolved problems in physics. It suggests that our understanding of the vacuum and dark energy is incomplete, requiring new theories or modifications to existing ones. Despite this problem, the cosmological constant remains the simplest explanation for the accelerating expansion. It fits well with current observations and provides a straightforward way to incorporate dark energy into the framework of general relativity. Alternative theories to the cosmological constant include dynamic fields like quintessence, which can change over time and space. These fields offer more flexibility in explaining the properties of dark energy, but also introduce additional complexity and parameters. The cosmological constant also plays a role in determining the ultimate fate of the universe. If it remains constant, the universe will continue to expand at an accelerating rate, leading to a big freeze, where galaxies move increasingly apart and the universe cools and fades. Understanding the cosmological constant is crucial for a complete picture of the universe's history and future. It influences the formation of cosmic structures, the behavior of galaxies, and the overall dynamics of the cosmos. Future observations and experiments aim to refine our measurements of the cosmological constant and explore its nature. Missions like the Euclid satellite and the Nancy Grace Roman Space Telescope will provide detailed data on the universe's expansion and the distribution of dark energy. The study of the cosmological constant bridges the gap between cosmology and quantum field theory, offering insights into the fundamental nature of space, time, and energy. As we delve deeper into this mysterious component of the universe, we may uncover new physics that challenges our current understanding. Observational evidence for the cosmological constant comes from multiple sources, each reinforcing the idea that dark energy is driving the universe's accelerated expansion. One of the most compelling pieces of evidence comes from the study of Type Ia supernovae. These supernovae are used as standard candles to measure cosmic distances. Observations show that these supernovae are dimmer than expected at large distances, indicating that the universe's expansion rate is increasing. The cosmic microwave background radiation, the afterglow of the Big Bang, provides another key piece of evidence. Precise measurements from satellites like COBE, WMAP, and Planck reveal temperature fluctuations that align with a universe containing a significant amount of dark energy. These fluctuations help determine the overall geometry and energy content of the universe, supporting the existence of the cosmological constant. Large-scale structure surveys, which map the distribution of galaxies and galaxy clusters, offer additional support. These surveys show patterns in the distribution of galaxies that are consistent with the influence of dark energy, affecting the growth and formation of cosmic structures over billions of years. Baryon acoustic oscillations, the regular periodic fluctuations in the density of the visible baryonic matter of the universe, also provide evidence. These oscillations serve as a standard ruler for measuring cosmic distances and expansion. Observations from surveys like the Sloan Digital Sky Survey show that the scale of these oscillations is consistent with a universe dominated by dark energy. Gravitational lensing, the bending of light from distant objects by massive structures like galaxy clusters, offers another method to measure the distribution of dark energy. Strong and weak lensing effects help map the mass distribution in the universe, revealing discrepancies that point to the presence of dark energy. The integrated Sachs-Wolf effect, which measures the change in energy of cosmic microwave background photons as they pass through gravitational potential wells, provides further evidence. This effect is enhanced in a universe with dark energy, leading to observable imprints on the cosmic microwave background. Observations of galaxy clusters, the largest gravitationally bound structures in the universe, also support the cosmological constant. The mass distribution and dynamics within clusters, inferred from X-ray observations and gravitational lensing, suggest the presence of an additional component beyond visible matter and dark matter. The Hubble constant, which measures the rate of expansion of the universe, has been determined with increasing precision through various methods. The tension between different measurements of the Hubble constant could potentially provide new insights into dark energy and the cosmological constant. Future missions and telescopes aim to gather more precise data on dark energy. The Euclid mission by the European Space Agency and NASA's Nancy Grace Roman Space Telescope will map the geometry of the universe and measure the effects of dark energy with unprecedented accuracy. Ground-based observatories like the Large Synoptic Survey Telescope, now known as the Vera C. Rubin Observatory, will conduct deep, wide-field surveys to study the distribution and behavior of dark energy over time. These observations will help refine our understanding of the cosmological constant. Theoretical models continue to evolve as new data is collected. Researchers explore various scenarios, including dynamic dark energy models like quintessence, to explain observations. These models introduce additional parameters and complexity but offer potential explanations for the observed acceleration. The cosmological constant also plays a role in understanding the ultimate fate of the universe. Depending on its properties, the universe could continue to expand forever, slow down, or even collapse in a big crunch. Observations help constrain these possibilities, guiding our understanding of cosmic evolution. The combination of observational techniques, from supernovae to cosmic microwave background measurements to large-scale structure surveys, provides a comprehensive picture of dark energy's influence. Each method contributes to a growing body of evidence supporting the cosmological constant. As technology advances, the precision and scope of observational evidence will continue to improve. New instruments and methods will enable even more detailed studies of dark energy, potentially revealing new aspects of the universe's fundamental nature. The quest to understand the cosmological constant and dark energy is one of the most exciting challenges in modern astrophysics. As we gather more evidence, we move closer to unraveling the mysteries of the universe's accelerated expansion and the underlying forces shaping its destiny. Theories of dark energy aim to explain the mysterious force driving the accelerated expansion of the universe. One of the simplest and most widely accepted theories is the cosmological constant, introduced by Einstein. It represents a constant energy density filling space homogeneously. Despite its simplicity, the cosmological constant raises significant questions. The value predicted by quantum field theory is vastly larger than what we observe, leading to the cosmological constant problem. This discrepancy suggests that our understanding of dark energy might be incomplete. Quintessence is an alternative theory proposing that dark energy is a dynamic field that evolves over time. Unlike the cosmological constant, quintessence can change in strength and distribution, offering a more flexible explanation for the accelerating expansion. Phantom energy is a variant of quintessence where the energy density increases over time, leading to a scenario known as the Big Rip. In this scenario, the universe's expansion accelerates to the point where galaxies, stars, and even atomic structures are torn apart. K-essence is another dynamic dark energy model that involves a scalar field with non-standard kinetic terms. This theory aims to address some of the issues with quintessence, providing a different mechanism for the acceleration of the universe. Modified gravity theories propose changes to general relativity to explain dark energy. These theories, such as FR gravity, suggest that the accelerated expansion is due to modifications in the gravitational interaction itself, rather than an additional energy component. Brainworld models, inspired by string theory, suggest that our universe is a three-dimensional brain, embedded in a higher dimensional space. The accelerated expansion could result from gravitational effects, leaking into or from these extra dimensions. Chameleon theories propose that the properties of dark energy vary depending on the local density of matter. In high-density regions, the effects of dark energy would be suppressed, while in low-density regions, like the cosmic voids, they become significant. The holographic principle suggests that the universe's accelerated expansion can be explained by a holographic description, where the physics of a three-dimensional volume is described by information on its two-dimensional boundary. This idea stems from attempts to reconcile quantum mechanics and gravity. Interacting dark energy models explore the possibility that dark energy and dark matter interact with each other. These interactions could modify the evolution of both components, leading to observable effects on the large-scale structure of the universe. Entropic gravity theories propose that gravity and dark energy arise from thermodynamic principles. According to this view, the expansion of the universe and the effects attributed to dark energy are consequences of entropy maximization in a gravitational system. Emergent gravity suggests that gravity and dark energy are emergent phenomena, arising from more fundamental microscopic processes. This theory aims to derive the behavior of dark energy from basic principles of statistical mechanics and quantum theory. Superfluid dark matter models combine aspects of dark matter and dark energy into a single framework. In these models, dark matter behaves like a superfluid with properties that could account for both the missing mass in galaxies and the accelerating expansion. The Chaplygin gas model is a theoretical approach that unifies dark matter and dark energy into a single substance. This exotic form of matter has properties that transition from behaving like dark matter at high densities to dark energy at low densities. As observational data improves, these theories are continuously tested and refined. Future missions and experiments, such as those involving next-generation telescopes and particle accelerators, will provide more insights into the nature of dark energy. Understanding dark energy remains one of the most profound challenges in modern physics. Each theory offers a unique perspective on this mysterious force, pushing the boundaries of our knowledge and guiding us toward a deeper comprehension of the universe's accelerating expansion. The discovery of dark energy and the accelerated expansion of the universe have profound implications for cosmology. These findings challenge our understanding of the cosmos and force us to rethink the dynamics and fate of the universe. One of the most significant implications is the realization that dark energy dominates the universe's energy content. Comprising about 68% of the total energy density, dark energy far outweighs the combined contributions of dark matter and ordinary matter. This dominance of dark energy means that the universe's expansion will continue to accelerate. The precise nature of this expansion depends on the properties of dark energy, which remain one of the biggest mysteries in cosmology. Dark energy also affects the rate at which structures form in the universe. The accelerated expansion opposes the gravitational collapse of matter, influencing the formation of galaxies, clusters, and large-scale structures. The presence of dark energy implies that the universe will not only expand forever, but will do so at an increasing rate. This scenario leads to a big freeze, where galaxies drift apart, stars burn out, and the universe becomes cold and dark. Understanding dark energy is crucial for the cosmic microwave background radiation. This afterglow of the Big Bang provides a snapshot of the early universe, and its detailed properties help constrain the amount and behavior of dark energy. The study of dark energy influences our models of cosmic inflation. Inflation is a period of rapid expansion in the early universe, and understanding dark energy could provide insights into the mechanisms that drove this inflationary phase. Dark energy's effect on the expansion rate helps calibrate the cosmic distance ladder. This ladder uses various astronomical objects to measure distances in the universe, and accurate distance measurements are essential for determining the Hubble constant. The nature of dark energy could provide clues about the fundamental laws of physics. It might point to new fields, particles, or forces that extend beyond the standard model, driving the development of new theories and experiments. Dark energy also impacts our understanding of dark matter. The interactions between dark energy and dark matter could influence the distribution and behavior of dark matter, affecting our models of galaxy formation and evolution. The implications for quantum gravity are profound. The relationship between dark energy and the fabric of spacetime might offer insights into a quantum theory of gravity, unifying general relativity and quantum mechanics. Dark energy challenges the notion of a static universe. Its discovery underscores the dynamic and evolving nature of the cosmos, where change and expansion are fundamental aspects of reality. Cosmological observations continue to test and refine our understanding of dark energy. Missions like Euclid and the Vera C. Rubin Observatory will provide high-precision data, helping to resolve questions about dark energy's properties and effects. The study of dark energy fosters interdisciplinary research, combining insights from astrophysics, particle physics, and theoretical physics. This collaboration is essential for developing a comprehensive understanding of the universe. As we probe deeper into the mysteries of dark energy, we advance our knowledge of the cosmos and its fundamental forces. Each discovery brings us closer to unraveling the ultimate fate of the universe and our place within it. Particle accelerators and experiments play a crucial role in probing the fundamental nature of matter and energy. These machines accelerate particles to high speeds and collide them to study the resulting interactions and particles. The Large Hadron Collider, or LHC, is the world's largest and most powerful particle accelerator. Located at CERN near Geneva, Switzerland, it has a 27-kilometer ring where protons are accelerated to near the speed of light before colliding. One of the LHC's major achievements was the discovery of the Higgs boson in 2012. This particle, predicted by the Standard Model, is responsible for giving other particles their mass through the Higgs field. Experiments at the LHC also search for evidence of dark matter. While dark matter particles have not yet been detected directly, the LHC can produce conditions that might reveal new particles or forces related to dark matter. The LHC conducts a variety of experiments, including ATLAS and CMS, which are general-purpose detectors designed to explore a wide range of physics. These experiments analyze the debris from proton collisions to search for new particles and phenomena. Another significant particle accelerator is the Tevatron, which operated at Fermilab in the United States until 2011. It was crucial in the discovery of the top quark and contributed to the search for the Higgs boson. Linear accelerators, like the Stanford Linear Collider, accelerate particles in a straight line and are used for precision experiments. These accelerators are essential for detailed studies of particle interactions and properties. The future of particle acceleration includes projects like the International Linear Collider and the Future Circular Collider, both of which aim to reach higher energies and explore new frontiers in particle physics. Particle accelerators are not limited to high-energy physics. Synchrotron light sources, such as the Advanced Photon Source, use accelerated electrons to produce intense X-rays for studying materials, biological structures, and chemical reactions. Neutrino experiments, like those conducted at Fermilab and the Super Kamiokande in Japan, use particle accelerators to generate neutrino beams. These experiments study neutrino oscillations and other properties, providing insights into one of the most elusive particles. Fixed target experiments involve directing a beam of accelerated particles at a stationary target. These experiments help study the behavior of particles and nuclei, contributing to our understanding of fundamental forces. Particle accelerators also explore the properties of quark-gluon plasma, a state of matter thought to have existed just after the Big Bang. Experiments at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory recreate these conditions to study this exotic state of matter. In addition to large-scale experiments, tabletop accelerators are being developed to study fundamental physics at smaller scales. These compact accelerators use advanced technologies to achieve high energies in a smaller footprint. The data from particle accelerator experiments is analyzed using complex computational techniques. Advances in machine learning and artificial intelligence are increasingly important for interpreting the vast amounts of data generated by these experiments. Particle accelerators and experiments continue to push the boundaries of our knowledge. They provide critical insights into the fundamental structure of matter, the forces governing the universe, and the potential existence of new physics beyond the standard model. As technology advances, these experiments will remain at the forefront of scientific discovery, exploring the deepest mysteries of the universe. Anomalous results in particle physics experiments often signal new physics or unknown phenomena. These unexpected findings challenge existing theories and prompt further investigation to understand their implications. One notable example of anomalous results is the measurement of the muon's magnetic moment. The muon G2 experiment at Fermilab found a discrepancy between the measured value and the prediction from the standard model. This deviation suggests potential new physics beyond the standard model. Another anomaly comes from the B-meson decays observed by the LHCb experiment at the Large Hadron Collider. The decay rates of these particles differ from standard model predictions, hinting at possible new particles or interactions. The ATLAS and CMS experiments at the LHC have also reported excess events that could indicate new particles. While these results have not yet reached the level of significance required for a discovery, they continue to be areas of active research. Neutrino experiments sometimes yield unexpected results as well. The LSND experiment at Los Alamos National Laboratory observed anomalies in neutrino oscillations that have led to the hypothesis of sterile neutrinos, a type of neutrino not accounted for in the standard model. Dark matter searches often report signals that are tantalizing but not conclusive. For example, the Dama Library experiment has observed an annual modulation in its data that could be interpreted as a dark matter signal, although other experiments have not confirmed this finding. Anomalies in cosmic ray observations also intrigue scientists. The AMS-02 experiment on the International Space Station has detected an excess of positrons in cosmic rays, which might be explained by dark matter annihilation or other astrophysical processes. The Xenon 1T experiment, designed to detect dark matter, recently reported an unexpected excess of low-energy events. This anomaly has led to various hypotheses, including the possible detection of solar axions or an unknown background. In condensed matter physics, the discovery of superconductivity at higher than expected temperatures presents an anomaly that challenges current understanding. Unconventional superconductors exhibit properties that defy the traditional BCS theory of superconductivity. The observation of the so-called cosmic void anomalies in large-scale structure surveys suggests regions of space with lower than expected matter density. These voids can provide insights into the distribution of dark matter and the nature of cosmic expansion. In particle collider experiments, discrepancies in the production rates of certain particles can point to new physics. For instance, the production rates of Higgs bosons or top quarks at different energies can reveal deviations from the standard model predictions. The detection of fast radio bursts, or FRBs, from distant galaxies remains an astronomical anomaly. These powerful bursts of radio waves have unknown origins, sparking various theories from exotic astrophysical objects to advanced alien civilizations. Some anomalies arise in the study of gravitational waves. While most detected signals are consistent with merging black holes or neutron stars, occasional events exhibit properties that are difficult to explain, suggesting the possibility of new astrophysical sources. Gamma-ray bursts, the most energetic events in the universe, sometimes display features that are not fully understood. Anomalous gamma-ray bursts challenge existing models of their progenitors and the mechanisms behind their immense energy release. Anomalous results often lead to new theories and models. They drive the scientific process by challenging established ideas and pushing the boundaries of what we know. Each anomaly represents a potential breakthrough in our understanding of the universe. Ongoing experiments and future research aim to resolve these anomalies. By exploring these unexpected findings, scientists hope to uncover new particles, forces, or phenomena that will reshape our understanding of the fundamental laws of nature. Supersymmetry, or SUSY, is a theoretical framework that extends the standard model of particle physics. It proposes a symmetry between fermions and bosons, predicting that each particle has a superpartner with different spin properties. The motivation for SUSY arises from several theoretical challenges in the standard model. One such challenge is the hierarchy problem, which concerns the large discrepancy between the weak force and gravitational force scales. Supersymmetry offers a solution by stabilizing the Higgs boson's mass against quantum corrections. In SUSY, each particle in the standard model has a superpartner. For instance, electrons have selectrons, quarks have squarks, and photons have photinos. These superpartners would help balance the forces and interactions at high energies. One of the appealing features of SUSY is that it provides candidates for dark matter. The lightest supersymmetric particle, often a neutralino, is stable and weakly interacting, fitting the profile of dark matter. Supersymmetry also offers potential explanations for the unification of forces. At high energy scales, the strengths of the electromagnetic, weak, and strong forces converge more naturally in SUSY, suggesting a grand unified theory. Despite its theoretical advantages, supersymmetry has not yet been observed experimentally. The Large Hadron Collider has searched for superpartners but has not found conclusive evidence, placing constraints on the mass ranges and properties of these particles. SUSY predicts that superpartners should have been produced in large numbers during the early universe. If they were heavy enough, they could have decayed into lighter particles, contributing to the dark matter observed today. Models of supersymmetry come in various forms. The Minimal Supersymmetric Standard Model, or MSSM, is the simplest extension, but there are also non-minimal models that introduce additional particles and interactions. SUSY could also impact cosmology and the early universe. For example, it might influence the dynamics of inflation, a rapid expansion that occurred just after the Big Bang, and help explain the observed density fluctuations in the cosmic microwave background. In addition to dark matter candidates, supersymmetry could provide insights into other unsolved problems in physics, such as the nature of neutrino masses and the matter-antimatter asymmetry in the universe. The search for SUSY involves multiple approaches. High-energy colliders like the LHC continue to probe higher energy scales, while indirect searches look for subtle effects of superpartners in precision measurements and rare decays. If supersymmetry is discovered, it would revolutionize our understanding of the fundamental particles and forces. It would extend the standard model and provide a deeper, more unified picture of the universe. Even in the absence of direct detection, supersymmetry remains a compelling framework. It drives the development of new theories and models, guiding experimental searches and providing a rich field for theoretical exploration. Critics of SUSY point out the lack of experimental evidence despite extensive searches. This has led to alternative approaches and models that address the same theoretical challenges without invoking supersymmetry. The future of SUSY research depends on both experimental advances and theoretical insights. As new data from colliders and other experiments become available, the constraints on SUSY models will become tighter, helping to refine or potentially rule out certain versions of the theory. The Large Hadron Collider, or LHC, is the world's most powerful particle accelerator, situated at CERN near Geneva. It has been instrumental in advancing our understanding of fundamental physics since it began operations in 2008. One of the LHC's most significant achievements is the discovery of the Higgs boson in 2012. This particle is a crucial part of the Standard Model, responsible for giving other particles their mass through the Higgs mechanism. The discovery of the Higgs boson confirmed the existence of the Higgs field, an energy field that permeates the universe. This finding was a major milestone in particle physics, providing critical validation for the Standard Model. The LHC has also made precise measurements of known particles and forces, helping to refine our understanding of the Standard Model. These measurements include properties of the Higgs boson, top quark, and W and Z bosons. One of the ongoing goals of the LHC is to search for new particles that could explain phenomena not accounted for by the Standard Model. This includes the search for supersymmetric particles, potential candidates for dark matter. In addition to searching for new particles, the LHC investigates the conditions of the early universe. By colliding heavy ions, it creates quark-gluon plasma, a state of matter thought to have existed just after the Big Bang. The LHC's experiments, such as ATLAS and CMS, have provided insights into rare particle interactions and decays. These experiments continue to push the boundaries of what we know about particle physics. The LHC has also explored the properties of the strong force, which binds quarks together to form protons and neutrons. Studies of proton-proton and heavy ion collisions have deepened our understanding of quantum chromodynamics, the theory describing the strong force. Another area of interest is the investigation of potential extra dimensions. Theories like string theory suggest that additional spatial dimensions could exist, and the LHC searches for signs of these dimensions through high-energy collisions. The LHCb experiment focuses on the differences between matter and antimatter. By studying the behavior of particles and their antiparticles, it seeks to understand why the universe is dominated by matter, despite the apparent symmetry in physical laws. Precision measurements at the LHC also test the limits of the Standard Model. Any deviations from predicted results could indicate new physics or interactions, guiding future theoretical and experimental research. The LHC's data is vast and requires sophisticated analysis techniques. Advances in machine learning and computational methods are crucial for processing and interpreting the results of LHC experiments. The discoveries made at the LHC have significant implications for other areas of physics, including cosmology and astrophysics. Understanding particle interactions at the smallest scales helps inform models of the universe at the largest scales. Future upgrades to the LHC, including the high-luminosity LHC, aim to increase its collision rate and sensitivity. These upgrades will enable even more precise measurements and the potential discovery of new particles. The LHC's contributions to science extend beyond particle physics. Its technology and methods have applications in fields like medical imaging, materials science, and data analysis, demonstrating the broad impact of fundamental research. As the LHC continues to explore the frontiers of physics, it remains a cornerstone of scientific discovery. Its experiments and findings drive the quest to understand the fundamental nature of reality, pushing the boundaries of human knowledge and innovation.
Beyond the Standard Model lies a realm of theoretical physics that seeks to address questions and phenomena that the Standard Model cannot fully explain. These efforts aim to develop a more comprehensive understanding of the fundamental forces and particles in the universe.
One of the primary motivations for going beyond the Standard Model is the inclusion of gravity. The Standard Model successfully describes 3 of the 4 fundamental forces, but it does not incorporate gravity, which is described separately by general relativity. String theory is one prominent framework that aims to unify all fundamental forces, including gravity. It proposes that particles are not point-like, but rather tiny, vibrating strings. Different modes of vibration correspond to different particles. Another significant area of research is the nature of dark matter. The Standard Model does not account for dark matter, which makes up about 27% of the universe. Theories beyond the Standard Model, such as supersymmetry, propose new particles that could be candidates for dark matter. Dark energy, responsible for the accelerated expansion of the universe, is another phenomenon not explained by the Standard Model. Theories like quintessence and modifications to general relativity aim to address this mysterious force. The matter-antimatter asymmetry observed in the universe is also unexplained by the Standard Model. While the Standard Model allows for some differences between matter and antimatter, it is insufficient to account for the dominance of matter over antimatter in the universe. Neutrino masses present another challenge. The discovery that neutrinos have mass implies the need for new physics beyond the standard model, as the original formulation assumes neutrinos are massless. Grand unified theories, or GUTs, attempt to unify the electromagnetic weak and strong forces into a single theoretical framework. These theories predict that at high energy scales, these forces merge into one, suggesting a more fundamental underlying symmetry. Extra dimensions are another intriguing concept. Theories like string theory and brain-world scenarios propose that additional spatial dimensions exist beyond the familiar three. These extra dimensions could have profound implications for particle physics and cosmology. Technicolor theories offer an alternative to the Higgs mechanism for giving particles mass. These theories propose new, strong forces and particles that dynamically generate the masses of the W and Z bosons without requiring a fundamental Higgs particle. Axions are hypothetical particles that could solve the strong CP problem in quantum chromodynamics and also serve as dark matter candidates. These particles are a focus of experimental searches and theoretical studies. The holographic principle suggests that all the information contained in a volume of space can be described by the information on its boundary. This idea, stemming from black hole physics and string theory, has implications for understanding quantum gravity. Loop quantum gravity is another approach to quantizing gravity, distinct from string theory. It proposes that space-time itself has a discrete structure at the smallest scales, potentially reconciling general relativity with quantum mechanics. Non-commutative geometry is an area of mathematics applied to physics, suggesting that space-time coordinates may not commute at small scales. This concept could lead to new insights into the nature of space-time and quantum field theory. The search for physics beyond the standard model drives much of modern theoretical and experimental physics. Each discovery and new piece of data helps refine these theories, bringing us closer to a more complete understanding of the fundamental nature of the universe. As research continues, the pursuit of knowledge beyond the standard model remains one of the most exciting and challenging frontiers in science. Loop quantum gravity, or LQG, is a theoretical framework that seeks to reconcile general relativity with quantum mechanics. Unlike string theory, which posits extra dimensions and vibrating strings, LQG focuses on quantizing spacetime itself. In LQG, spacetime is not continuous, but composed of discrete, finite loops. These loops form a network known as a spin network, where the geometry of space is quantized. This discrete nature implies that space and time have a fundamental smaller scale, known as the Planck length. The primary goal of LQG is to understand the quantum properties of gravity. It attempts to provide a quantum theory of gravity without the need for extra dimensions or supersymmetry, setting it apart from other approaches like string theory. One of the key predictions of LQG is that spacetime is granular at the smallest scales. This granularity leads to the concept of spin foam, a dynamic version of spin networks that describes the evolution of spacetime over time. LQG has significant implications for our understanding of black holes. It suggests that the singularity at the center of a black hole, where density becomes infinite, is replaced by a quantum region with finite quantized spacetime. This could potentially resolve the problem of singularities in general relativity. Another important aspect of LQG is its potential to explain the origin of the universe. The theory proposes that the Big Bang could be replaced by a Big Bounce, where a previous contracting universe rebounds into the current expanding one, avoiding the singularity predicted by classical general relativity. LQG also offers insights into the nature of entropy and the thermodynamics of black holes. It predicts that black hole entropy is proportional to the area of the event horizon, providing a quantum gravitational explanation for the Bekenstein-Hawking entropy formula. Experimental verification of LQG remains a significant challenge due to the extremely small scales involved. However, researchers are exploring potential observable consequences, such as modifications to the cosmic microwave background radiation or the propagation of gravitational waves. The mathematics of LQG involve as complex structures like Ashtekar variables, which reformulate general relativity in terms of connections and loops. These variables simplify the equations of gravity, making them more amenable to quantization. LQG has inspired various related approaches, such as loop quantum cosmology, which applies the principles of LQG to cosmological models. This field aims to understand the early universe and cosmic inflation within a quantum gravitational framework. Despite its successes, LQG faces several open questions. One challenge is to recover the familiar, smooth spacetime of general relativity from the discrete structures of LQG at larger scales, a process known as the classical limit. Another area of research is the unification of LQG with the standard model of particle physics. Integrating matter fields and forces into the loop quantum gravity framework remains an ongoing effort, with various models and approaches under investigation. LQG also explores the potential connections with other approaches to quantum gravity. For example, researchers investigate possible links between LQG and string theory or non-commutative geometry, seeking a deeper understanding of quantum space-time. The development of LQG has profound philosophical implications. It challenges our classical notions of space and time, suggesting that at the most fundamental level, reality is composed of discrete, quantized units rather than a continuous fabric. As research in LQG progresses, it continues to push the boundaries of theoretical physics. By attempting to unify the principles of quantum mechanics and general relativity, LQG represents a significant step towards a more complete understanding of the fundamental nature of the universe. M-theory is an advanced framework in theoretical physics that attempts to unify all consistent versions of superstring theory. It emerged in the mid-1990s, largely due to the work of physicist Edward Witten and others, who discovered that the 5 previously known string theories were actually different limits of a single, more fundamental theory. M-theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can have different modes of vibration, each corresponding to a different particle. Unlike string theory, which operates in 10 dimensions, M-theory requires 11 dimensions. One of the key insights of M-theory is the concept of branes. Branes are multidimensional objects, with the simplest being one-dimensional strings. Higher dimensional branes, such as membranes or three-branes, can exist within this framework, providing a rich structure for the theory. M-theory has the potential to unify all fundamental forces, including gravity. It incorporates the principles of quantum mechanics and general relativity, aiming to create a consistent theory of quantum gravity. This unification is one of the main goals of theoretical physics. The additional dimension in M-theory allows for more complex interactions and structures. This 11th dimension can manifest in various ways, leading to different physical phenomena and providing a deeper understanding of the universe's fabric. Dualities are a crucial aspect of M-theory. These are mathematical transformations that reveal the equivalence between seemingly different physical theories. Dualities show that different string theories are just different perspectives of M-theory, strengthening the idea of a single underlying framework. M-theory also suggests the existence of higher dimensional spaces, known as Calabi-Yau manifolds. These spaces are essential for compactifying the extra dimensions, making the theory consistent with our observable four-dimensional universe. The study of M-theory has led to the concept of the multiverse. This idea proposes that our universe is just one of many, each with its own physical laws and constants. These multiple universes could arise from different ways of compactifying the extra dimensions in M-theory. One of the major challenges in M-theory is its mathematical complexity. The theory involves highly sophisticated mathematics, making it difficult to derive concrete predictions that can be tested experimentally. However, ongoing research continues to explore its implications. M-theory has provided new insights into black holes. It predicts that black holes should have properties consistent with both quantum mechanics and general relativity, potentially resolving some of the paradoxes associated with black hole information and entropy. The theory also has implications for cosmology, particularly in understanding the early universe and cosmic inflation. M-theory could provide a framework for explaining the rapid expansion of the universe immediately after the Big Bang. Despite its promise, M-theory is still a work in progress. Many aspects remain speculative, and a complete formulation has yet to be achieved. Researchers continue to develop the theory, seeking a more comprehensive understanding of its principles and predictions. M-theory's potential to unify all physical theories has made it a focal point of theoretical physics. Its rich structure and mathematical elegance offer a profound vision of the universe's underlying principles, inspiring ongoing research and exploration. Critics of M-theory point out the lack of direct experimental evidence. The theory's predictions often occur at energy scales far beyond the reach of current technology. This has led to debates within the scientific community about the empirical validity of such high-level theoretical constructs. Nevertheless, M-theory represents a bold step towards a unified theory of everything. As research advances and new mathematical tools are developed, the hope is that M-theory will continue to provide deeper insights into the fundamental nature of reality, guiding us towards a more complete understanding of the universe. Grand Unified Theories, or GUTS, aim to unify the three fundamental forces of the Standard Model: the electromagnetic, weak and strong nuclear forces. These theories propose that at high energy scales, these forces merge into a single, more fundamental force. One of the main motivations for GUTS is the observation that the strengths of these three forces appear to converge at high energy levels. This suggests that they may be different manifestations of a single underlying force. A central concept in GUTS is the idea of symmetry breaking. At extremely high temperatures, such as those present just after the Big Bang, the unified force would exist. As the universe cooled, this symmetry broke, separating into the distinct forces we observe today. GUTS predict the existence of new particles and interactions beyond the Standard Model. These include X and Y bosons, which mediate transitions between quarks and leptons, leading to phenomena such as proton decay. Proton decay is a key prediction of many GUTS. If protons can decay, it would provide strong evidence for the unification of forces. Experiments like Super Kamiokande in Japan search for signs of proton decay, although none have been observed so far. One of the simplest GUTS is based on the symmetry group SU5. This model extends the Standard Model by grouping particles into larger multiplets, predicting new interactions and particles. However, SU5 has been ruled out by experiments due to the lack of observed proton decay. Another GUT is based on the symmetry group SO10. This theory unifies all Standard Model particles into a single representation and naturally includes right-handed neutrinos, which can explain the small masses of observed neutrinos through the seesaw mechanism. The Pati-Salam model is another GUT framework. It introduces an additional symmetry between quarks and leptons, predicting leptoquarks, particles that can mediate transitions between quarks and leptons. This model offers a different perspective on unification. GUTS also provide potential solutions to the hierarchy problem. By unifying forces at high energies, these theories can offer explanations for why the weak force is much stronger than gravity, and why the Higgs boson mass is stable against large quantum corrections. The search for GUTS involves both theoretical and experimental efforts. High-energy particle colliders, like the Large Hadron Collider probe energy scales, that could reveal signs of grand unification. Future colliders with even higher energies might be needed to test these theories directly. Cosmology offers another avenue for testing GUTS. The conditions of the early universe, such as during cosmic inflation, could produce relics or imprints that inform us about grand unification. Observations of cosmic microwave background radiation and large-scale structure help refine these models. GUTS have implications for dark matter. Some models predict new particles that could serve as dark matter candidates, offering potential links between particle physics and cosmology. Despite their potential, GUTS face significant challenges. One major issue is the lack of experimental evidence for proton decay and other predicted phenomena. This has led to the development of more sophisticated models and the exploration of alternatives. String theory provides a broader framework that can incorporate GUTS. In string theory, grand unification emerges naturally from the compactification of extra dimensions, suggesting a deeper connection between these theories. The ongoing search for GUTS represents a quest for a deeper understanding of the universe's fundamental forces. By seeking to unify the forces of nature, GUTS aim to provide a more elegant and comprehensive picture of the physical world, guiding future research and discovery. As experimental capabilities advance, the hope is that evidence for grand unification will emerge, offering new insights into the nature of reality. Experimental challenges in physics often drive innovation and technological advancements. One of the primary challenges is detecting extremely rare events, such as interactions between dark matter particles and ordinary matter. These events are so infrequent that experiments must be highly sensitive and well shielded from background noise. Another significant challenge is achieving the necessary energy levels to probe fundamental particles and forces. Particle accelerators like the Large Hadron Collider operate at the highest energies ever achieved, but some theories predict phenomena at energy scales beyond current capabilities. Precision measurements are also crucial. Many theories beyond the standard model predict subtle deviations from known physics. Detecting these deviations requires experiments with extraordinary precision, such as those measuring the magnetic moments of particles or the properties of neutrinos. Neutrino experiments face the challenge of studying particles that interact very weakly with matter. Large detectors, often placed deep underground or underwater, are needed to observe neutrino interactions. These detectors must filter out a vast amount of background noise to identify genuine neutrino events. Gravitational wave detection is another area with significant experimental challenges. Gravitational waves are incredibly faint, requiring detectors like LIGO and Virgo to measure minute distortions in spacetime. These detectors must isolate themselves from all forms of environmental noise, such as seismic activity and human interference. Proton decay, predicted by many grand unified theories, has not yet been observed. Experiments like Super Kamiokande in Japan continue to search for this rare process, but the predicted lifetimes of protons are so long that detecting decay events requires extremely large detectors and extended observation periods. Dark energy remains one of the biggest mysteries in cosmology. Understanding its nature and properties involves precise measurements of the universe's expansion rate and the distribution of galaxies. This requires large-scale surveys and advanced telescopes capable of observing distant celestial objects with high accuracy. The search for extra dimensions, as proposed by string theory and other models, also presents experimental challenges. These dimensions might only reveal themselves at very high energies, or through indirect effects, making them difficult to detect with current technology. Building and maintaining large-scale experiments like the Large Hadron Collider involve significant logistical and financial challenges. These projects require international collaboration, substantial funding, and sophisticated infrastructure to construct and operate. Data analysis poses its own set of challenges. Experiments like those conducted at the LHC generate vast amounts of data that must be processed and analyzed. Advanced computational techniques, including machine learning and artificial intelligence, are increasingly used to sift through this data and identify meaningful patterns. Cryogenic technology is essential for many modern experiments, particularly those searching for dark matter or studying cosmic microwave background radiation. Maintaining extremely low temperatures over long periods is technically challenging and requires specialized equipment and expertise. Interdisciplinary collaboration is often necessary to overcome experimental challenges. Physicists, engineers, computer scientists, and other experts must work together to design, build, and interpret the results of cutting-edge experiments. Environmental factors such as cosmic rays, natural radioactivity, and even human activity can interfere with delicate measurements. Shielding experiments from these influences while maintaining accessibility and functionality is a complex task. Theoretical uncertainties also complicate experimental physics. Predictions from theories beyond the standard model often come with large uncertainties, making it difficult to design experiments that can definitively confirm or refute these theories. Despite these challenges, the drive to explore fundamental questions about the universe continues to push the boundaries of technology and human ingenuity. Each challenge represents an opportunity for discovery, innovation, and deeper understanding, fueling the ongoing quest to unravel the mysteries of the cosmos. Modified Newtonian dynamics, or MOND, is an alternative theory proposed to explain the observed discrepancies in galaxy rotation curves without invoking dark matter. It was introduced by physicist Mordechai Milgram in the early 1980s. The central idea of MOND is that Newton's laws of motion need to be modified at very low accelerations. According to MOND, the force of gravity does not follow the inverse square law at these small accelerations, which are common in the outer regions of galaxies. MOND suggests that when the acceleration due to gravity drops below a certain threshold, the relationship between force and acceleration changes. This modified relationship can account for the flat rotation curves of galaxies, where stars in the outer regions move faster than expected based on visible matter alone. One of the key successes of MOND is its ability to predict the rotation curves of spiral galaxies with remarkable accuracy, using only the distribution of visible matter. This predictive power has made MOND a compelling alternative to dark matter in explaining certain galactic dynamics. Despite its successes, MOND faces significant challenges. One major issue is its difficulty in explaining the observed behavior of galaxy clusters. The total mass inferred from the motions within clusters still exceeds what can be accounted for by visible matter, even with MOND's modifications. MOND also struggles to explain the cosmic microwave background radiation and the large-scale structure of the universe. These phenomena are well explained by the standard cosmological model, which includes dark matter and dark energy, but MOND requires additional modifications or new components to fit these observations. To address some of these challenges, extended versions of MOND have been proposed, such as TVES, tensor vector scalar gravity. TVES is a relativistic theory that aims to incorporate MOND's principles into a framework compatible with general relativity, providing a more complete description of gravitational phenomena. Another approach to modifying MOND involves the concept of emergent gravity. This theory, proposed by Eric Verlinde, suggests that gravity arises from changes in the information associated with the positions of material bodies, potentially explaining the effects attributed to dark matter. Despite the ongoing debates and challenges, MOND has provided valuable insights into the behavior of galaxies and has prompted further investigation into the nature of gravity and inertia. It highlights the need for alternative approaches and continued exploration of fundamental physics. Experimental tests of MOND involve precise measurements of galaxy rotation curves, gravitational lensing, and the dynamics of galaxy clusters. These tests aim to distinguish between the predictions of MOND and those of the dark matter paradigm, providing critical data for evaluating these theories. The study of MOND also intersects with investigations into dark energy. Some researchers explore whether the modifications to gravity proposed by MOND could also account for the accelerated expansion of the universe, potentially linking the two phenomena. While MOND remains controversial, it serves as a valuable reminder of the importance of questioning established theories and exploring alternative explanations. Its successes and limitations both contribute to the broader effort to understand the fundamental forces governing the universe. The ongoing dialogue between proponents of MOND and dark matter theories enriches the scientific process. By challenging each other's assumptions and predictions, researchers push the boundaries of knowledge and refine their models to better match observational data. Future observations and experiments, such as those conducted by next-generation telescopes and space missions, will provide more data to test the predictions of MOND and its variants. These efforts will help determine whether MOND can be reconciled with a broader range of cosmic phenomena. As we continue to investigate the mysteries of the universe, MOND stands as a testament to the creativity and perseverance of scientists seeking to unravel the complexities of cosmic dynamics. Whether it ultimately proves to be a stepping stone or a cornerstone, MOND's contributions to the field of physics are undeniable. Brain cosmology is an intriguing framework within string theory that suggests our universe exists on a three-dimensional brain, a membrane-like structure, within a higher dimensional space. This idea provides a new perspective on fundamental physics and cosmology. The concept of brains arises naturally in string theory, which posits that the fundamental building blocks of the universe are one-dimensional strings rather than point particles. These strings can also manifest as higher dimensional objects, called brains. In brain cosmology, our observable universe is confined to a three-dimensional brain. However, gravity can propagate into the higher dimensional bulk, providing a potential explanation for why gravity is so much weaker than the other fundamental forces. One of the most significant implications of brain cosmology is the possibility of extra dimensions. These additional spatial dimensions, beyond the familiar three, could have profound effects on the behavior of gravity and other forces at small scales. The Randall-Sundrum model is a well-known example of brain cosmology. This model proposes a warped extra dimension, which can explain the hierarchy problem, the large discrepancy between the strengths of gravity and the other fundamental forces. In the Randall-Sundrum model, gravity is localized near a brane in a higher dimensional bulk. This localization could result in gravity appearing much weaker in our three-dimensional universe, offering a potential solution to the hierarchy problem. Brane cosmology also has implications for the early universe and cosmic inflation. The interactions between branes in the higher dimensional bulk could drive the rapid expansion of the universe, providing a new mechanism for inflation. Another fascinating aspect of brane cosmology is the possibility of brane collisions. These collisions could create new universes or alter the properties of existing ones, leading to a multiverse scenario where different branes represent different universes with varying physical laws. The study of black holes in brane cosmology offers unique insights. Black holes on the brane could have different properties than those in four-dimensional general relativity, potentially leading to observable differences in their behavior and signatures. Brane cosmology can also impact our understanding of dark matter and dark energy. The effects of extra dimensions and brane interactions could provide alternative explanations for these mysterious components of the universe. One of the challenges of brane cosmology is finding experimental evidence for extra dimensions. High-energy particle colliders, such as the Large Hadron Collider, search for signs of extra dimensions through deviations from expected particle interactions and the production of new particles. Cosmological observations, such as the cosmic microwave background and large-scale structure surveys, can also provide constraints on brane cosmology models. These observations help refine the parameters of the models and test their predictions. The ADS-CFT correspondence, a theoretical framework within string theory, has connections to brane cosmology. This correspondence suggests a relationship between a higher dimensional gravitational theory and a lower dimensional conformal field theory, offering new insights into the nature of gravity and quantum mechanics. Despite its speculative nature, brane cosmology has stimulated significant research and discussion. It challenges conventional ideas about space, time, and dimensions, pushing the boundaries of our understanding of the universe. As theoretical and experimental techniques advance, the study of brane cosmology will continue to explore the potential existence and effects of extra dimensions. Whether or not extra dimensions are ultimately confirmed, the insights gained from brane cosmology enrich our quest to understand the fundamental nature of reality. The holographic principle is a groundbreaking concept in theoretical physics that proposes all the information contained in a volume of space can be described by information on the boundary of that space. This principle suggests that our three-dimensional universe might be encoded on a two-dimensional boundary, much like a hologram. This idea first emerged from studies of black hole thermodynamics. Physicists Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole, which is a measure of its information content, is proportional to the area of its event horizon, not its volume. This was a surprising result, indicating a fundamental connection between information and surface area. The holographic principle was further developed by physicist Gerard 't Hooft and later by Leonard Susskind. They proposed that this principle could apply not just to black holes, but to the entire universe. In essence, all the physical processes occurring within a volume of space could be represented by data encoded on the boundary of that volume. One of the most significant realizations of the holographic principle is the ADS-CFT correspondence. This correspondence, discovered by Juan Maldacena, posits a relationship between a gravitational theory in a higher dimensional anti-de Sitter, ADS, space, and a conformal field theory, CFT, on the lower dimensional boundary. This duality has provided deep insights into quantum gravity and string theory. The ADS-CFT correspondence suggests that a higher dimensional theory with gravity can be equivalent to a lower dimensional theory without gravity. This duality has been used to tackle problems in both quantum field theory and quantum gravity, providing a powerful tool for theoretical physicists. One of the implications of the holographic principle is that space and time might not be fundamental. Instead, they could emerge from more basic, underlying degrees of freedom encoded on a lower dimensional surface. This challenges our conventional understanding of the fabric of the universe. The holographic principle also offers potential solutions to the black hole information paradox. This paradox arises because information that falls into a black hole seems to be lost forever, contradicting the principles of quantum mechanics. The holographic principle suggests that this information is not lost, but rather encoded on the event horizon, preserving the laws of quantum mechanics. In cosmology, the holographic principle provides a novel way of thinking about the universe. It implies that the vast amount of information contained within our observable universe could be represented by data on a distant cosmic boundary. This perspective could lead to new approaches to understanding the origins and structure of the cosmos. The principle has also found applications in condensed matter physics. Researchers use holographic techniques to study strongly interacting systems, such as those found in materials with unconventional superconductivity. These techniques offer new ways to model and understand complex quantum systems. Despite its successes, the holographic principle remains a highly theoretical concept. Experimental verification is challenging, as it requires observations that can directly test the relationship between higher dimensional theories and their lower dimensional counterparts. However, advances in technology and observational techniques may provide indirect evidence. For instance, studies of the cosmic microwave background or gravitational waves could reveal signatures consistent with holographic models of the universe. The holographic principle continues to inspire new research and ideas in fundamental physics. It encourages scientists to explore the deep connections between gravity, quantum mechanics, and information theory, leading to a more unified understanding of the natural world. As research progresses, the holographic principle might offer new insights into the nature of space-time, the behavior of black holes, and the fundamental structure of reality. It remains one of the most intriguing and promising concepts in the quest to understand the universe. The implications of the holographic principle extend beyond physics, touching on philosophical questions about the nature of reality and our perception of the world. It challenges us to rethink our assumptions and explore new ways of understanding the cosmos. In conclusion, the holographic principle represents a profound shift in our understanding of the universe. By proposing that our three-dimensional reality might be a projection from a two-dimensional boundary, it opens up exciting possibilities for future discoveries and a deeper comprehension of the fundamental laws governing existence. Non-commutative geometry is a branch of mathematics that extends the concepts of geometry to spaces where coordinates do not commute. In classical geometry, the coordinates of a point in space can be measured simultaneously and independently. However, in non-commutative geometry, the order in which you measure coordinates affects the outcome. The idea of non-commutative geometry arises naturally in quantum mechanics, where the position and momentum of a particle are described by operators that do not commute. This non-commutativity is encapsulated in the Heisenberg uncertainty principle, which states that certain pairs of physical properties cannot be simultaneously measured with arbitrary precision. Non-commutative geometry was developed more formally by mathematician Alain Connes. Connes' approach generalizes the notion of space by using algebraic structures where the geometry of space is encoded in the algebra of functions defined on that space. This framework allows for the extension of geometric and topological concepts to settings where the traditional notions of points and distances may not apply. In the context of physics, non-commutative geometry provides a natural framework for understanding certain aspects of quantum field theory and string theory. It offers new ways to describe the geometry of spacetime at the Planck scale, where classical concepts of space and time break down due to quantum effects. One of the key motivations for studying non-commutative geometry is its potential to reconcile general relativity with quantum mechanics. By treating spacetime coordinates as non-commuting operators, non-commutative geometry provides a mathematical framework that could incorporate both gravitational and quantum phenomena. Non-commutative geometry has also been applied to the Standard Model of particle physics. In this context, it offers a way to unify the description of fundamental particles and forces, potentially providing insights into the structure of matter and the origin of mass. The concept of non-commutative spacetime suggests that at very small scales, the smooth fabric of spacetime is replaced by a discrete, quantized structure. This idea is consistent with other approaches to quantum gravity, such as loop quantum gravity and string theory, which also propose discrete structures at the Planck scale. One of the intriguing predictions of non-commutative geometry is the possibility of modifying the usual notion of distance. In non-commutative spaces, the distance between points can depend on the order in which measurements are made, leading to new geometric properties and potentially observable effects. Experimental searches for evidence of non-commutative geometry involve looking for deviations from classical predictions in high-energy physics experiments. These deviations could manifest as tiny shifts in the behavior of particles or fields at very small scales, providing clues about the underlying structure of space-time. Non-commutative geometry also has implications for cosmology. It could offer new perspectives on the early universe, cosmic inflation, and the nature of singularities, such as the Big Bang and black holes. By providing a framework for describing space-time at extremely high energies, it helps address some of the most fundamental questions in cosmology. The mathematical tools of non-commutative geometry, such as operator algebras and spectral triples, have found applications beyond theoretical physics. They are used in various areas of mathematics, including functional analysis, differential geometry, and topology, demonstrating the broad relevance and utility of this approach. Non-commutative geometry encourages the exploration of new physical theories and models. By challenging the conventional notions of space and time, it opens up possibilities for developing more comprehensive and unified descriptions of the natural world. The study of non-commutative geometry continues to evolve, with ongoing research aimed at refining its mathematical foundations and exploring its physical implications. As new discoveries are made, this field promises to provide deeper insights into the nature of reality and the fundamental principles that govern the universe. In conclusion, non-commutative geometry represents a significant extension of traditional geometric concepts, offering a powerful framework for understanding the quantum nature of space-time. By integrating the principles of quantum mechanics with geometric structures, it paves the way for new discoveries and a deeper comprehension of the universe's underlying fabric. Emergent gravity is a theoretical framework, suggesting that gravity is not a fundamental force, but an emergent phenomenon arising from the underlying microscopic degrees of freedom of space-time. This concept is inspired by thermodynamics and statistical mechanics, where macroscopic properties emerge from the collective behavior of microscopic constituents. One of the key proponents of emergent gravity is physicist Eric Verlinde. In 2010, Verlinde proposed that gravity could be an entropic force resulting from changes in the information associated with the positions of material bodies. According to this view, gravity emerges from the statistical behavior of microscopic degrees of freedom encoded on a holographic screen. Verlinde's theory builds on the holographic principle, which posits that all the information contained within a volume of space can be described by information on its boundary. In this framework, gravity arises as an emergent phenomenon when one considers the entropy and information content of the holographic screen. Emergent gravity offers a new perspective on dark matter. Verlinde proposed that what we perceive as dark matter might be a manifestation of additional gravitational effects arising from the underlying microscopic structure of space-time. This idea challenges the traditional view that dark matter is a form of unseen matter. One of the strengths of emergent gravity is its ability to derive Newton's laws and Einstein's field equations from thermodynamic principles. By considering the entropy and temperature associated with a holographic screen, Verlinde showed how gravitational forces could naturally emerge from these statistical properties. The concept of emergent gravity has also been applied to black holes. In this context, black hole thermodynamics, which relates the entropy and temperature of a black hole to its horizon area, can be understood as a manifestation of the microscopic degrees of freedom of space-time. Emergent gravity provides a potential resolution to the black hole information paradox. If gravity and space-time are emergent phenomena, then the information that falls into a black hole could be preserved in the microscopic degrees of freedom, avoiding the paradox of information loss. The study of emergent gravity intersects with various other approaches to quantum gravity, such as loop quantum gravity and string theory. These theories also suggest that space-time and gravity are not fundamental, but arise from more basic underlying structures. Experimental tests of emergent gravity involve looking for deviations from classical predictions in the behavior of galaxies, galaxy clusters, and cosmic structures. If emergent gravity can account for the effects attributed to dark matter, it could provide a new explanation for these observations. Cosmology offers another avenue for testing emergent gravity. By examining the large-scale structure of the universe, the cosmic microwave background, and the distribution of galaxies, researchers can look for signatures consistent with the predictions of emergent gravity. One challenge for emergent gravity is to fully explain all the phenomena attributed to dark matter, such as the rotation curves of galaxies and the behavior of galaxy clusters. While Verlander's theory provides some promising results, further refinements and extensions are needed to match all observations. Emergent gravity also has implications for our understanding of space and time. If space-time is emergent, it suggests that the fabric of the universe is fundamentally different from what we experience at macroscopic scales, with new properties emerging from microscopic interactions. The idea of emergent gravity encourages a rethinking of the nature of forces and interactions. It suggests that other fundamental forces, such as electromagnetism and the nuclear forces, might also have emergent properties arising from deeper underlying principles. Research in emergent gravity continues to explore these ideas, seeking to develop a more complete theoretical framework and to identify observable consequences. As our understanding of the microscopic structure of space-time improves, emergent gravity could provide a new paradigm for understanding the universe. In conclusion, emergent gravity offers a novel and potentially transformative perspective on the nature of gravity and space-time. By proposing that these phenomena arise from underlying microscopic degrees of freedom, it challenges conventional views and opens up new avenues for theoretical and experimental research in fundamental physics. In this video, we explored some of the most intriguing concepts and theories in modern physics, starting with the limitations of special relativity in explaining all aspects of our universe. We discussed how it fails to account for gravitational effects and does not align with quantum mechanics, which governs the very small. We then delved into the mysteries of dark matter and dark energy, highlighting how these enigmatic components of the universe remain largely unexplained by current physical theories. The evidence for dark matter, particularly through galactic rotation curves, emphasizes the need for new physics or particles beyond what we currently understand. The potential candidates for dark matter, such as WIMPs, were examined, as well as the various experimental searches designed to detect them. Despite the challenges, the pursuit of understanding these particles continues to drive advancements in technology and methodology. We also explored the fascinating realm of alternative theories like MOND and their implications for our understanding of gravity and cosmology. These theories challenge conventional views and offer new ways to interpret the gravitational behavior of galaxies and cosmic structures. In the realm of high-energy physics, the Large Hadron Collider's contributions were discussed, including its role in discovering the Higgs boson and searching for new particles that could provide insights into physics beyond the standard model. We then ventured into the speculative but compelling theories of quantum gravity, including loop quantum gravity and M-theory. These frameworks seek to reconcile general relativity with quantum mechanics, offering profound insights into the nature of space, time, and the universe. The concept of the holographic principle was introduced, suggesting that our three-dimensional universe might be a projection from a two-dimensional boundary, a theory that challenges our fundamental understanding of reality. Non-commutative geometry was also discussed, providing a framework where the traditional notions of space and time are replaced by quantized structures, leading to potential new physics at very small scales. Emergent gravity offered another revolutionary perspective, proposing that gravity is not a fundamental force, but arises from the collective behavior of microscopic degrees of freedom. This idea has significant implications for understanding dark matter, black holes, and the very fabric of the universe. Finally, we covered grand unified theories and the experimental challenges facing modern physics. These efforts aim to unify the fundamental forces and particles, pushing the boundaries of our knowledge and technology. Thank you for joining us on this journey through some of the most fascinating topics in physics. If you enjoyed this video, please like and subscribe to our channel. Don't forget to check out our other videos for more in-depth explorations of the mysteries of the universe. Your support helps us continue to bring you high-quality content on the latest discoveries and theories in science.